Imagine a situation where several extraordinary and seemingly unbelievable events occur within a very short period of time. Over the course of just 36 hours, two of the brightest stars in the universe could suddenly explode, becoming visible to anyone who simply looks up at the sky. During the same period, two powerful earthquakes could strike the surface of Venezuela, capable of shaking the entire country and even affecting neighboring regions. And to top it all off, the famous interstellar object known as 3IATLAS Atlas could be subjected to a solar storm, illuminating the sky with a fiery glow and ejecting a coronal mass. All of this, astonishingly, would happen within just 32 days. If such a scenario were written by science fiction writers, editors might consider it too absurd and unrealistic, as it seems too incredible even for fictional stories. However, reality, as it turns out, is presenting us with exactly this kind of synchronized chain of events, which could serve as the basis for a film of the future, so unusual and striking it is. This series of events appears not merely as a coincidence but as a real challenge to our conventional notions of nature and the laws governing the universe. Tonight, together, we will try to understand each of them, carefully examining the scientific foundations underlying phenomena related to stellar flares and planetary disturbances. We are approaching a dangerous boundary, where coincidences begin to be perceived as signs of something greater than mere chance. Do not disconnect, because everything we learn about the events that took place on September 25th could challenge our usual views of what happens in the heavens and on Earth, forcing us to reconsider many of our beliefs about the nature of what is occurring. Now, let's proceed step by step, starting with the first part. Thus, the chain of incredible events begins with two simultaneous stellar explosions in space, the brightest and most visible to observers on Earth. At the same time, beneath our feet on the surface of the planet, in the southern part of South America, in Venezuela, two powerful earthquakes occur, each exceeding a magnitude of 6 on the Richter scale. These earthquakes tear the ground apart, causing destruction and panic among the population. And all of this happens within just a few days, literally over a few days, at the end of September 2025. And at the same time, and this is particularly astonishing, another incredible event takes place in space. The interstellar object known as 3IATLAS Atlas, a mysterious cosmic visitor that has long attracted the attention of scientists, is subjected to a solar storm, a powerful flow of magnetized plasma ejected from the sun at an incredible speed, over 1,000,000 miles per hour. A fiery eruption of solar activity, recorded by satellites, indicates that solar storms are intersecting with something unusual, something that does not fit into conventional scientific models. And all of this is happening simultaneously: star explosions, earthquakes, and solar storms, creating an incredible synchronicity of events that seems more like a theatrical production than reality. If someone were to put such a scenario into a movie, it would be considered too fantastical, too unbelievable. But this is precisely the astonishing picture unfolding before our eyes at the end of the 21st century. This synchronicity is not merely coincidence, it prompts us to consider what lies behind it, hidden connections, patterns that we have not yet fully understood. And perhaps, right now, at this very moment, we are witnessing the beginning of a new era when science will need to reconsider its views and expand the boundaries of its knowledge. However, all of this will be discussed a little later. For now, let's carefully examine each of these phenomena. Between September 23 and 25, Venezuela once again recorded a series of powerful eruptions and earthquakes, events that at first glance seem random. However, within the context of modern astronomy and geophysics, they raise increasingly many questions about possible links between cosmic and terrestrial processes. At the same time, models designed to predict coronal mass ejections have repeatedly demonstrated their effectiveness, showing peak activity precisely within this specified timeframe. Against this backdrop, a unique object was discovered, named 3I Atlas, which was identified just 2 months ago by the Asteroid Terrestrial Impact Last Alert System, a system specializing in monitoring potentially hazardous asteroids and interstellar bodies. This object, similar to its predecessor, Oumuamua, passed through the inner regions of the solar system, which could coincide with the most active period of the 25th solar cycle, considered one of the most dynamic and variable in the history of solar observations. The geography of these natural and cosmic phenomena is astonishing in its scale and complexity. New eruptions prominently appeared in the constellations of Centaurus and Sagittarius, which are primarily visible from the southern hemisphere and often remain inaccessible to observers from northern latitudes. The light emitted from these stellar events traveled for thousands of years before finally reaching our eyes exactly during this remarkable and eventful week. Earthquakes, in turn, occurred near the Mna Grande region, located in northwestern Venezuela, an area deeply tectonically complex, where the boundaries of the Caribbean and South American tectonic plates collide, causing intense geodynamic activity. During this collision, the coronal mass ejections spread through the inner heliosphere, a vast, volumetric region of space that extends beyond Jupiter's orbit. Regarding object 3I Atlas, its trajectory passed through the plane of the ecliptic, an imaginary disk where a significant portion of planetary activity in our solar system is concentrated. It crossed this plane between Mars and the Sun, moving along a path that includes many possible scenarios of interaction with solar and interstellar phenomena. It is important to emphasize that at this stage, we are not making definitive conclusions about causal relationships between the observed events. Doing so would be premature and possibly even irresponsible, as science requires careful and verified hypotheses. Instead, we are creating a map of clusters, developing detailed documentation of the interstellar objects approach, and attempting to correlate widely accepted scientific explanations with more daring, hypothetical assumptions that could open new horizons in understanding space and its interactions with Earth. The United States Geological Survey states that, to date, there is no confirmed data linking space weather, that is, solar flare activity, with seismic phenomena on Earth's surface. However, solar physicists do not hide the fact that coronal mass ejections are a natural and often predictable aspect of solar activity, especially during solar maximum periods. Astronomers studying stellar processes consider new flares to be quite predictable, although they note that predicting their exact timing and strength in each specific case is an extremely complex task. Some associate these phenomena with the evolution of binary star systems, but within the current scientific paradigm, such connections require further confirmation. So, what makes this week particularly unique in the context of modern astronomy and space research? The answer lies in the discovery of the interstellar object designated 3I Atlas, which has become only the third confirmed interstellar body ever recorded, following the discovery of Oumuamua in 2017. By the end of October, specifically on the 29th, the planet gas giant known as 3I Atlas will reach its closest approach to the Sun during its orbit. At that moment, it will be at a distance of 136 astronomical units from the star, still beyond Earth's orbit but close enough for scientists using ground-based telescopes to study its composition and behavior in real time. This level of observation offers unique opportunities to gather data on the composition and dynamics of this distant planet, as well as its atmosphere and internal structure, which was previously nearly impossible due to vast distances and technical limitations. The geometric situation for observations becomes even more favorable on December 29, when 3 asteroids will make their closest approach to Earth in their entire existence, at a distance of exactly 1 astronomical unit. In this case, they will be closer than Mars at its farthest point in its orbit, providing astronomers and enthusiasts with an opportunity to observe them without much difficulty. For several months, from mid-autumn to the end of winter, both professional observatories and amateur astronomers, even those equipped with modest telescopes, will be able to witness this spectacular event. It should be noted that this season also coincides with an increase in space weather, which is related to certain astronomical and geophysical factors. The autumn equinox, which occurs at the end of September, triggers the so-called Russell-McFerran effect, a unique geometric feature of Earth's magnetic field orientation, where its structure enhances the interaction between the magnetosphere and the solar wind. As a result, geomagnetic disturbances and solar flares intensify. It is during the period from September to November that the brightest and most impressive auroras of the year are observed, along with the most significant manifestations of space weather, which can affect satellite operations, power grids, and other technologies related to our planet. The promise we make to our readers and viewers is that we will provide not only precise scientific explanations of these processes but also detailed scenarios of possible developments. We will try to answer the question, what if? And we will clearly distinguish each hypothesis, what is confirmed by observations, what is an assumption, and what is science fiction. All the information we share matters because wonder and science go hand in hand. Sometimes, the most honest stance that modern science can take is to admit, we do not yet know the full truth, but we observe and study. Pay special attention to these points because, if coronal mass ejections can knock tails off comets that have been orbiting our sun for millennia, then what will they do to an object that has spent millions of years traveling through interstellar space, carrying ice and dust formed in entirely different star systems? We will soon find out the answer, and it may be truly astonishing. Next, we will discuss sudden stellar explosions and double novae that brightly illuminated the southern sky at a time when Earth's crust began to shake and tremble. This is the second part of our story. In the pre-dawn hours of September 23, 2025, an amateur astronomer named John Sitch, who has been scanning the southern horizons from his observatory on Chatsworth Island in New South Wales for many years, will share his observations. This time, his attention was focused on the sky, and what he discovered in that early hour soon caused widespread resonance. His find attracted the interest not only of astronomy enthusiasts but also of scientific satellites such as gamma-ray, X-ray, and high-energy telescopes located throughout the solar system. This discovery became a recent observation recorded by NASA's Fermi Gamma Ray Space Telescope, which generated genuine excitement among astronomers and star phenomena enthusiasts. This powerful instrument detected a flux of high-energy photons emanating from the nova region, serving as important evidence of processes occurring under extreme conditions in space. At the same time, the orbiting observatory SWIFT, specifically designed to search for gamma-ray bursts, turned its X-ray telescope toward the constellation Centaurus and began recording intense emission of hard X-ray spectrum. These signals indicated the most vigorous acceleration of particles, electrons and protons, in the expanding shock wave of the nova, pointing to the presence of physics at the very edge of high-energy phenomena. These were not merely bright flashes that astronomy lovers enjoy observing from their yards or local observatories. No, these were crucial signs that a true physical test was underway deep within space, where the laws of nature manifest under conditions surpassing all our earthly understanding. Electrons and protons reached speeds close to that of light, creating conditions for unique physical processes. Magnetic fields present in these regions twisted into incredible knots, forming a complex and luminous magnetosphere. Temperatures in these zones soared to millions of degrees, unambiguously indicating high-energy activity. But even these impressive events did not end there. Just a few days after this spectacular astronomical event, which drew the attention of specialists and enthusiasts alike, cosmic activity surged once more. Over 7,094 fathoms from Earth, a new star erupted, a flare that reached a brightness level of 62 on the detection scale. These two stellar explosions, both recorded by the same observer, were bright enough to be seen even with small telescopes or binoculars. And both occurred within the same astonishing week, which was a real surprise for professional astronomers. Although novae are not such rare phenomena in our galaxy, averaging about 10 to 12 such events per year, witnessing two bright flares reaching near visible brightness within just a few days is truly exceptional. This rare occurrence is so impressive that it will be remembered by many specialists and enthusiasts for years to come. The last time spectacular displays of two bright novae occurred within a single summer season was in the 20th century. Before that, it might have been worth going back a few years to find similar events. The physics underlying these powerful outbursts tells a complex and fascinating story of stellar cannibalism unfolding on the scale of the entire universe. Each nova begins with a white dwarf, a dense, hot core of a dead star roughly the size of Earth, yet with a mass that can equal or exceed that of our Sun. This dense remnant orbits a normal star that gradually loses hydrogen from its outer atmosphere. Over years, centuries, and sometimes thousands of years, gas continuously accumulates on the surface of the white dwarf, becoming increasingly dense and hot under the influence of immense gravitational compression. When temperature and pressure reach a critical point, the accumulated hydrogen begins to undergo uncontrolled thermonuclear fusion, causing a powerful explosion, a flare that can increase the system's brightness by tens of thousands of times. This explosion does not completely destroy the white dwarf but rather blows off its surface layer, returning the system to a state of gradual matter accumulation. Some novae can recur at predictable intervals, flaring every few decades, while others remain dormant. These relativistic particles, generated by powerful cosmic events, actively interact with magnetic fields and the surrounding environment, leading to the formation of high-energy photons. Such photons have been detected through observations conducted by the Fermi and Swift space missions. The physics behind this process is the same as that operating in the most extreme conditions of the universe, in the remnants of supernova explosions and in the cores of active galactic nuclei. In these cosmic cataclysms, incredible transformations of matter occur, converting it into intense high-energy radiation. These mechanisms also produce and propagate high-energy photon pulses, which we can observe and record from Earth. For observers in the southern hemisphere, both nova events are favorably positioned for detailed study. In particular, the nova of 1935 in the constellation Centaurus is located quite far south of the equator, making it more difficult to observe for those in northern latitudes. Residents of northern regions must wait until this celestial object rises above the southern horizon to observe it well. A similar situation applies to nova V7794 Sagittari, situated in the constellation Sagittarius. This star has a similar southern observation geometry. For those located in moderate northern latitudes, it appears low on the southern horizon, while south of the equator it is high in the sky, making it much easier to observe. The process of discovering such objects vividly demonstrates the importance of collaboration in modern astronomy, especially when studying variable stars. Initial observations made by an astronomer named Sitch, which were reported through the International Astronomical Union's Central Bureau, sparked a series of further investigations and observations. Circular number 5611 confirmed the original discovery of a nova in 1935 in Centaurus, and circular number 5612 recorded and verified the appearance of a new star in the constellation Sagittarius, V7994 Sagittari. Within days of the discovery, scientists and astronomical observatories around the world began conducting photometric observations aimed at precisely measuring the brightness of these new objects, as well as spectroscopic studies. These observations revealed characteristic spectral lines, especially lines of hydrogen, helium, and heavier elements, indicating expanding shells of the novae. Such spectra help scientists better understand the physical nature of the processes occurring. Amateur astronomers, as well as professional astronomers, play a vital role in this process. Organizations like the American Association of Variable Star Observers organize regular monitoring and observation of these objects. Their daily observations allow for tracking changes over time, specifically the light curves showing how the brightness of the nova evolves after the outburst. These curves are complex. They display phases of rapid brightness increase, a plateau, a period of stable brightness, and a gradual decline that can last from several months to several years. Such data provide crucial insights into the physical mechanisms underlying the explosion, as well as the properties of the system in which the event occurs. Professional telescopes, despite their power and precision, cannot continuously monitor every brightness change of newly formed stars in real time. Therefore, dedicated amateur astronomers, observing these objects night after night, provide unique data that significantly expand our understanding of such cosmic phenomena. Regarding the system of numbering and naming these objects, it often causes confusion among newcomers to astronomy. Part 8 of 73. Nova in the constellation Centaurus has been officially designated as the 1935th variable star, while V7994 Sagittari is a star in the constellation Sagittarius. The question that inevitably concerns those who are seriously fascinated by the mysteries of space and unexpected manifestations of space weather boils down to the following. Is there really some connection between stellar explosion outbursts occurring in the same week as significant geomagnetic disturbances on Earth? In other words, could these seemingly coincidental cosmic events, happening at the same time, be part of a more complex and interconnected picture than mere coincidence? From an astronomical perspective, the answer to this question appears quite obvious. The bright flares we call novas occur in neighboring constellations, often located thousands of light-years from our planet. They certainly do not pose a direct threat to Earth and do not have any noticeable impact on phenomena occurring here. The energy of these cosmic explosions, despite their colossal scale from a human perception standpoint, disperses into interstellar space over vast distances. As a result, it reaches Earth as a very small, almost imperceptible increase in the photon flux. This radiation, which is beautiful and interesting to observe but harmless to human perception. Nevertheless, the very idea that within a single week, double explosions could occur in binary star systems coinciding with two major earthquakes and passing through active periods of solar activity seems truly astonishing and mysterious. Perhaps the best and most honest answer to this is to acknowledge that both science and observed coincidences require careful evaluation and analysis, as well as an understanding of the physics underlying these processes. At the same time, one cannot exclude the possibility that the universe sometimes arranges events in such a way that these coincidences resemble poetic metaphors, reminders of how subtly and wonderfully interconnected the cosmos and our lives are. Meanwhile, several thousand miles away from any observatory capable of recording these stellar fireworks and explosions, underground, in the most solid and stable part of the Earth's surface, a different story was unfolding. Specifically, in Venezuela, in the state of Sucre, at a certain moment in time, it seemed as if not only a mysterious connection between space and terrestrial phenomena was being demonstrated, but also more grounded, tangible manifestations of nature's power. And that is precisely what will be discussed in the next part of our story, about the earthquake that shook this country. On September 22, at exactly 21 hours 55 minutes and 35 seconds Coordinated Universal Time, a powerful earthquake occurred. The significance of this event lies in the fact that the Earth's crust in the Suluya region released energy equivalent to several nuclear explosions, essentially causing a sudden and very strong tremor. The earthquake's magnitude reached 6.12, which is considered significant in seismology, and its epicenter was located just 24 kilometers east-northeast of Mine Grande. The destruction caused by this event occurred at a relatively shallow depth, 0.8 kilometers, sufficient for the tremor to be felt even in nearby buildings. Waves radiating from the fault line traveled at approximately 6 kilometers per second, passing through bedrock and reaching populated areas within seconds of the quake itself. As a result, residents of cities from Maracaibo to Caracas, as well as in border towns in Colombia and coastal regions of the Caribbean basin, felt the ground beneath their feet begin to sway, windows shake, chandeliers sway, and houses tremble. Millions of videos appeared on social media showing distressed people evacuating buildings. In total, the two crustal collisions during this period released an amount of energy equivalent to that of a single earthquake with a magnitude of approximately 6.4 or 6.5. This indicates a significant release of energy, which, even considering the scale of global seismic activity, warrants special attention. These events on September 24 and 25 were the most powerful manifestations of seismic activity in the region in recent years, surpassing the earthquake recorded in Kamchatka on September 18 with a magnitude of 7.8. Thus, these two earthquakes in Venezuela became among the most notable and powerful global seismic events at the end of September 2005. To add even more drama to these occurrences, subsequent aftershocks followed, intensifying the sense of tension and uncertainty. On September 25, a quake of approximately 0.58 magnitude occurred in the same region, which, despite being relatively modest compared to the main shock, still contributed to additional destruction and heightened anxiety among the population. This is because such successive underground tremors are typically accompanied by decay patterns characteristic of marine faults and are anticipated by seismologists after major seismic events. These models suggest that after the main shock, a series of smaller but still dangerous tremors may follow. In this case, despite the fact that the magnitude of the second event ranged from 0.58 to 0.6, its consequences were significant enough to cause additional damage and maintain a level of concern among local residents, already alarmed by two major earthquakes within a short period of time. The explanation for this phenomenon lies in the features of regional tectonics. The Maracaibo Basin, located in a complex and tense zone where the Caribbean plate contacts the South American plate, is an area saturated with a network of faults. Among them, particular importance is attached to faults such as Bacona, Ancan, and Santa Marta. These geological boundaries, the borders between two lithospheric plates, have accumulated substantial stresses over many years, decades, or even centuries, forming energy that ultimately must be released in the form of sudden shifts and displacements of the Earth's crust. It is these accumulated stresses that are the cause of powerful earthquakes in this region. It is worth noting that the difference in depth between the two main seismic events, about 7 to 8 kilometers versus 14 kilometers, plays a crucial role in the strength and nature of the earthquakes. Shallow tremors generally cause stronger and more noticeable ground vibrations because seismic waves passing less deeply have fewer opportunities to disperse and weaken. As a result, such shallow earthquakes, like the one that occurred on September 24, create the sensation of powerful underground shocks both in Venezuela and in neighboring countries, including Colombia. Regarding the precise measurements of magnitude, various seismological agencies provided slightly different estimates. For example, the United States Geological Survey initially recorded the first tremor with a magnitude of approximately 6.2, while the European Mediterranean Seismological Center and other international organizations, using their own analysis methods, reported values ranging from 6.1 to 6.3. These discrepancies are explained by differences in the methods used to determine magnitude, data interpretation models, as well as updates that occurred as new information from numerous seismic stations became available. Additionally, differences pertain to the ways of measuring the magnitude. Despite initial reports indicating relatively minor structural damage given the magnitude, specialists assessing the consequences of the natural event continued their work for several days after the occurrence. Their task was not only to document the visible damages manifested in infrastructure and residential buildings but also to assess the potential long-term impact that this earthquake could have on the stability and strength of structures. Historically, this region is known for its heightened seismic activity. In particular, the complex tectonic structure surrounding Lake Maracaibo, as well as the broader boundaries separating the Caribbean and South American lithospheric plates, are responsible for regular earthquakes. Although such natural disasters occur quite frequently, the magnitude of specific events, like the recent one, is often irregular. Geological studies indicate that major faults in this region frequently serve as sources not only of immediate earthquakes but also can trigger additional active processes in adjacent fault zones. This mechanism, known as stress transfer, occurs because one earthquake alters the stress field in neighboring fault systems, thereby increasing the likelihood of new underground tremors. In the days and weeks following the main event, both professional seismologists and local residents paid close attention to analyzing and monitoring potential aftershocks. The question facing experts and the population is whether additional strong earthquakes are possible in the near future. The answer to this question is ambiguous. Statistical data show that after a major earthquake, subsequent tremors are usually observed and are considered a normal part of seismic activity. The strongest among them typically occur within the first few days or weeks after the main event. However, despite accumulated knowledge and numerous studies, seismologists cannot provide an absolute guarantee that a more powerful earthquake will not occur in the same area in the near future. The field of earthquake prediction remains one of the most complex in modern science, despite decades of research into the patterns of stress accumulation in the Earth's crust, analysis of precursor phenomena, and the application of sophisticated statistical methods. International monitoring systems continuously track each subsequent earthquake, creating a comprehensive picture of how the fault system responded to the stress changes caused by the two major faults. The database known as the Global Centroid Moment Tensor began conducting detailed analyses of fault orientations, slip directions, and rupture mechanisms for both events, helping seismologists understand which fault segments actually moved and how the stress field was altered across a broader region. For residents of Zulia State and nearby areas, the double earthquake served as a stark reminder of the geological reality of their region. The seriousness of the situation was underscored by the tests to which building codes, emergency preparedness systems, and response services are subjected, ensuring the safety of the population. Moderate damages recorded after the earthquake are likely related to the fortunate coincidence of the timing of the event. It occurred during hours when most people were at home rather than at potentially vulnerable workplaces. This, along with continuous improvements in construction standards and emergency response systems, played a role in minimizing destruction. A broader question arising from this event concerns its temporal connection with other natural phenomena that occurred during the week in which the earthquake took place. Many experts believe that, to date, there is no scientific evidence of any physical mechanism linking solar activity, space weather, or astronomical events with the occurrence of earthquakes. Therefore, any attempts to establish a direct connection between these phenomena remain unconfirmed, and the scientific community continues to investigate the causes and patterns of seismic activity. The official position of the United States Geological Survey clearly emphasizes, no scientifically confirmed links between space weather and seismic activity have been established to date. This means that, although statements about correlations between these phenomena often appear in scientific literature and mass media, such claims remain unverified and are met with serious skepticism among specialists. At the same time, the human mind is naturally inclined to seek patterns, especially during periods when dramatic and noticeable events occur that coincide in time or place. This is why situations arise where double new moons, double earthquakes, active solar weather, or even the passage of an interstellar object through the inner solar system are perceived as interconnected events, despite the fact that the mechanisms of their interaction remain unclear and require further study. Perhaps the most honest scientific approach is to record the sequence of events, create detailed timelines, analyze each phenomenon separately, and remain open to possible connections, avoiding the temptation to assume causal relationships where only correlation exists. For now, after a series of powerful shocks that continued to shake the consciousness of Venezuelans, solar activity has prepared a new chapter in this story, reminding us that the surroundings of Earth can be just as dynamic and unpredictable as its solid surface. The fourth part of this story is dedicated to solar activity, which reached its peak energy levels during those days. Millions of miles above the Earth, trembling under the influence of powerful storms, our star, the Sun, was performing its own explosive displays, creating a bright and destructive symphony of solar eruptions. During the same days when the sky over South America was illuminated by flashes of stellar explosions, and the ground trembled with deafening shocks caused by earthquakes, coronal mass ejections, some of the most powerful manifestations of solar activity were occurring on the Sun's surface. Clouds of magnetoplasma, weighing billions of tons, surged into space like gigantic jets of energy, crossing paths with various objects within and beyond the inner solar system. These ejections are among the most intense and destructive phenomena known to humanity. Within our system, such eruptions originate in the Sun's corona, the thin, bright, and highly active outer layer of the star, where magnetic field lines twist, tangle, and ultimately snap, much like overstressed rubber bands. During magnetic reconnection, an enormous amount of energy is released, equivalent to billions of hydrogen bombs, accelerating plasma clouds to speeds ranging from 250 to 3,000 kilometers per second. These velocities enable such clouds to traverse the distance between the Earth and the Sun in just 1 to 4 days, making them particularly dangerous to our planet and its technological infrastructure. NASA's Space Weather Prediction Center employs sophisticated computer models, among which the WSL model stands out, a powerful simulation designed to track and forecast the propagation of coronal mass ejections. This model considers parameters such as solar wind, magnetic field density, and orientation, allowing predictions of when and where these plasma clouds will reach spacecraft, planets, and other objects along their paths. In late September of the year 2025, models predicted active conditions. Several coronal mass ejections, or CMEs, were passing through the inner solar system over a span of days, coinciding with dates when Earth experienced double new moons and double earthquakes. And then something unprecedented in human history occurred. For the first time in recorded observations, one of these solar storms encountered an object born in another star system. This interstellar object, moving along a retrograde orbit inclined approximately 175 degrees to the ecliptic plane, crossed the same region of space in which our planet orbits. This zone is particularly vulnerable to collisions with various solar phenomena, such as solar wind, coronal mass ejections, and other forms of solar activity. That is why there are examples in the history of astronomy where such interactions have led to noticeable changes in the behavior of comets and other interstellar objects. It has long been known in scientific circles that when coronal mass ejections collide with comets, very bright and well-documented events occur. These are not mere assumptions or speculations. They are results confirmed by physical measurements and observations made with satellites and space probes, as well as detailed descriptions in peer-reviewed scientific literature. For instance, in 2007, the European Space Agency launched satellites capable of precisely monitoring solar activity and its consequences. During their mission, they recorded how a coronal mass ejection, or CME, completely detached the ion tail of Comet Encke. This event lasted several hours and served as a vivid demonstration that the magnetic field formed between the solar plasma and the comet's material is a rather fragile structure. During this incident, the magnetic connection between the solar wind and the comet's material underwent significant changes, and the comet's ion tail was entirely disconnected, torn off, and dispersed into space. At the same time, new tails formed from the residual material left after this event, indicating that the interaction processes do not cease but continue to renew themselves. Comets have two types of tails, each formed by different physical mechanisms and responding to solar influence in their own way. The so-called curved or plasma tail, shaped by solar radiation, gently bends away from the sun, pushed by the pressure of solar radiation. This tail consists of microscopic particles that, under the influence of sunlight, receive a gentle but constant acceleration, resulting in the characteristic curve. In contrast, the ion tail extends straight away from the sun, following the lines of the magnetic field embedded in the solar wind, a stream of charged particles emanating from our star. When a CME collides with this magnetic field, significant changes occur. The ion tail can completely detach, move away from the comet, and ultimately disintegrate, while new tails form from fresh material ejected by solar activity. Regarding specific hypotheses that the interstellar visitor, tentatively designated as TriAI, was affected by a coronal mass ejection, such conclusions are primarily based on trajectory analysis using specialized models rather than direct observations. These models allow for the prediction of possible interaction scenarios, but there is always an element of uncertainty. In particular, solar weather forecasts indicate that in the second half of September, the trajectories of solar storms could have intersected with the path of this interstellar object. However, it is important to remember that modern space weather models are quite effective at predicting general trends related to the movement of solar storms, but they struggle with accurately determining the details of such interactions. Therefore, despite confidence in forecasts, it is not possible to completely rule out the possibility that the interaction could have occurred differently or gone unnoticed. If the interaction indeed took place as predicted by the models, we could expect a number of noticeable and potentially measurable consequences. For example, an increase in ionization around the interstellar visitor could make the gas dust clouds surrounding its core brighter due to enhanced light emission. Additionally, changes in the morphology of the ion tail, such as bending or interaction, could occur. The interaction of the space object, named Atlas, with the solar environment is a complex and fascinating physical process based on magnetic reconnection mechanisms. This same mechanism underlies phenomena such as solar flares and geomagnetic storms, which have a significant impact on our planet and its near-Earth space. When a stream of solar plasma, rich in twisted magnetic field lines, encounters the comet's ionosphere, a region filled with ions and electrons created by the interaction of the solar wind with its material, magnetic field lines can connect, disconnect, and reconnect again, releasing energy that quickly converts into the kinetic energy of charged particles. This process, captured in a delicate and elegant physical picture, causes particle acceleration and produces various observable phenomena, flares, radiation, and other effects that enhance our understanding of the interaction between solar activity and interstellar objects. All of this occurs dynamically, in real time, with the magnetic field topology constantly changing, allowing the stored magnetic energy to be transformed into the motion energy of charged particles and into radiation detected by our instruments and observation tools. The object, named Atlas, is more than just another target for space weather research. It holds a special place in our system of cosmic objects as the third confirmed interstellar body, following the discoveries of Oumuamua in 2017 and Borisov in 2019. These interstellar objects are not only unusual cosmic bodies but also carriers of information about materials formed around other star systems billions of years ago. Atlas contains materials that originated in other stellar systems and may have spent a long time in the interstellar medium before encountering its path. When it comes to interactions with solar activity, solar storms and coronal mass ejections can influence the behavior and properties of this interstellar object. We are witnessing the first recorded case where a clear direct impact of our Sun on interstellar material located beyond our system has been observed, material belonging to another stellar neighbor passing through interstellar space. The geometry of this cosmic visitor's trajectory makes such interactions more likely than with previous interstellar objects. Unlike Oumuamua, which quickly traversed the inner solar system along a highly inclined orbit relative to the ecliptic plane, the 3IATLAS objects are moving along a path that keeps them close to this plane, where most solar activity is concentrated and where Earth experiences the greatest effects of space weather. The current solar cycle, the 25th, has provided an active background for such interactions. This cycle reached its peak during the 24th and 25th years, leading to an increase in sunspots, the frequency of solar flares, and more frequent coronal mass ejections. The onset of this solar cycle coincided with the period when the 3IATLAS objects are subjected to solar activity in its most intense phase. As a result, they are exposed to heightened space weather conditions that interstellar visitors have not previously experienced. To confirm the interaction with coronal mass ejections, a thorough analysis of changes in the object's brightness, spectroscopic characteristics, and morphological alterations occurring over timescales from several hours to several days is necessary. Such studies require data from professional observatories as well as observations by amateur astronomers worldwide, who actively monitored the state of the 3IATLAS objects at the end of September. While preliminary results are still under analysis, final conclusions require further research. However, the implications of this event extend beyond mere observation. If we manage to document recent weeks and months of cosmic events, it will seem as if they are woven into an unusual and complex fabric of a timeline that challenges conventional notions of order and regularity in the world around us. In this kaleidoscope of phenomena, we observe a variety of events: stellar explosions, earthquakes, solar storms, and interactions with interstellar visitors, as if all these occurrences coincidentally converged in time, creating an illusion of chaos and randomness. But was this truly a coincidence, or is there a deeper pattern hidden within, which will become clearer as our journey progresses? Specifically, the planet we will refer to as the 3IATLAS objects continues its path, approaching the flyby of Mars scheduled for October 3rd. At this moment, observations are being made of any possible changes that could occur under the influence of solar coronal mass ejections, powerful streams of energy capable of affecting our neighboring interplanetary world and possibly the planet Earth itself. These events are just part of a broader picture that has been unfolding in the final days of September 2025, when numerous unusual phenomena, seemingly unrelated at first glance, were occurring in space. It is worth pausing for a moment to consider what exactly we are trying to track and understand amidst this chaos. We are presented with astonishing scenes: double explosions in the starry skies visible to the naked eye, double earthquakes occurring within a few hours of each other, coronal mass ejections passing through the inner layers of the solar system, and an interstellar visitor crossing our vicinity during the peak of solar activity. All these are events happening very rapidly, often within a week or even less, creating the impression that the universe is teeming with energy and in a state of flux. During this period, there is a compression of time and events, making them particularly vivid and noticeable to scientists and observers alike. When discussing such phenomena, it is important to remember that scientific practice involves certain understandings and guidelines for their interpretation. For example, the authoritative United States Geological Survey states that, to date, there is no convincing evidence that space weather, solar storms, coronal mass ejections, and similar phenomena is directly linked to earthquakes or other geological catastrophes. Decades of research aimed at finding correlations between solar activity and seismic events have failed to identify reliable patterns that could be used to forecast earthquakes based on cosmic factors. Professional seismologists emphasize that predicting an earthquake with high accuracy using current methods is virtually impossible, whether through analysis of precursors on Earth or influences from extraterrestrial sources. This view is supported by numerous scientific studies and observations that show no direct connection between cosmic activity and seismic dynamics. Similarly, astronomers studying stars regard new objects as natural consequences of evolutionary processes within binary systems. Specifically, when white dwarfs accumulate material from their stellar companions, this can lead to nuclear explosions, so-called novae or supernovae. The timing of such outbursts is strictly governed by the laws of stellar evolution and does not depend on solar or terrestrial influences. Examples can include objects such as V1935 Centauri and V7994 Sagittari, which are common, though very bright, representatives of processes that occur regularly throughout our galaxy. These phenomena are nothing more than part of the natural cycle of stellar life, and they happen regardless of what is occurring on the Sun or within our solar system. Regarding solar processes, solar physicists consider coronal mass ejections as a natural consequence of the evolution of the magnetic field in the solar corona. These ejections, however, do not diminish the importance of recognizing and confirming fundamental scientific principles. They do not mean ignoring the astonishing nature of the temporary assemblage we call the universe. Sometimes, the very structure of the universe aligns in such a way that events appear to be synchronized, even if the mechanisms underlying these phenomena remain simple and ordinary. An important question arises: how can we maintain a balance in our perception between the necessity of skepticism and the ability to genuinely marvel? This is precisely the challenge we set for ourselves in this study. In our scientific practice, we will strictly adhere to clear boundaries between different types of statements and conclusions. For example, we will distinguish between observed facts, measurements of physical quantities, and the coordinates of locations. It is the observational data and measurement results, such as spectroscopic discoveries, that will form our foundation. These are what instruments, satellites, seismographs, telescopes, have objectively recorded and confirmed. Based on this solid foundation, we will build layers of interpretations and theoretical models grounded in verified physics and well-supported theories. Beyond this domain, where scientific facts turn into assumptions and hypotheses, lies the zone of speculation. In this zone, we will proceed very carefully and with clear labeling. What is a hypothesis and what is an established fact? Among such hypotheses are possible links between solar activity and phenomena on Earth, hypothetical influences of stellar events on the dynamics of the solar system, or mechanisms connecting cosmic processes with geological changes. All these ideas deserve investigation. However, it is crucial to maintain transparency and clearly distinguish that they are merely hypotheses, not confirmed facts. For the general audience, it is necessary to provide clear definitions of terms related to cosmic events. For example, a nova is an event where, as a result of a thermonuclear explosion on the surface of a white dwarf, the brightness of a binary star system increases by thousands or even millions of times. In contrast, a supernova is a situation where the explosion completely destroys the star, transforming it into a cloud of gas and dust. An important cosmic phenomenon is the ejection of a coronal mass, massive clouds of plasma, weighing billions of tons, expelled by the Sun at speeds ranging from several hundred to several thousand kilometers per second. Perihelion is the point in the orbit of any object closest to the Sun. An astronomical unit is the average distance between the Earth and the Sun, approximately 93 million miles or 150 million kilometers. Ion tails of comets form when the solar wind strips electrons from gas molecules in their comae, creating charged particles that follow magnetic field lines directly away from the Sun. These tails can extend millions of kilometers into space, serving as visible evidence of the invisible magnetic and electromagnetic processes occurring between stars and smaller celestial bodies. In our research, we will strictly distinguish observed phenomena from imaginary connections, while maintaining respect for both scientific rigor and human curiosity. We will examine in detail the physics of stellar explosions, earthquakes, and interactions of solar storms. During our work, we will track the 3-day passage of the spacecraft designated as ITLS past Mars on October 3 and its approach to perigee on October 29. We will analyze legitimate scientific hypotheses regarding links between cosmic and terrestrial phenomena, while also exploring more exotic ideas and assumptions that require caution and clear labeling as hypotheses. The autumn equinox period is traditionally accompanied by an increase in space weather effects, driven by a complex interplay of natural factors and phenomena. During this season, phenomena such as the Russell effect and the McFerrin effect become particularly pronounced, both related to the interaction between solar wind and Earth's magnetic field. These interactions often lead to heightened geomagnetic activity in September and October, creating conditions conducive to storms and magnetic disturbances. This seasonal intensification essentially adds important context to the observed rise in space weather activity at the end of September, regardless of other factors or phenomena, as this period provides optimal conditions for solar and magnetic activity to manifest. In this context, the unique scientific potential of the interstellar object known as 3IATLAS becomes especially significant, as it is the third confirmed interstellar visitor observed and systematically studied by us. For the first time in history, it was observed during a period of high solar activity, opening new horizons for understanding interstellar bodies, their interactions with the solar wind, and the cosmic environment. The geometric configuration of its trajectory, passing near the ecliptic plane, the region where most of the solar system's activity is concentrated, significantly increases the chances of obtaining valuable data. In this context, observations from multiple interplanetary missions become particularly important, as only joint efforts allow for the most comprehensive recording of the structure and behavior of the interstellar object, as well as its interactions with the space environment. Unlike objects such as Oumuamua, which quickly disappeared from view, or Borisov, which remained at a distance, the 3IATLAS provide a unique opportunity for long-term observation spanning several months. This greatly enhances the potential for scientific analysis and a more complete understanding of its physical characteristics and behavior under conditions of intense solar activity. The prospects for October and November go beyond purely academic interest. For example, missions orbiting Mars, such as the European Space Agency's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter, plan targeted observations during the flyby in early October. These studies could potentially deliver unprecedented images of the core and structure of the interstellar visitor, significantly expanding our knowledge of its components and features. On Earth, as space cosmological research advances, ground-based observatories worldwide continue to monitor changes in brightness, spectroscopic evolution, and morphological variations of the interstellar object, as well as their dependence on solar weather. These observations help us understand how solar activity influences interstellar material and its properties as it approaches Earth. In particular, studying the dynamics of brightness and spectrum allows us to detect the reactions of interstellar matter to solar flares and magnetic storms, which is crucial for understanding the overall picture of cosmic environment interactions. Regarding earthquakes, for example, in Venezuela, the sequence of aftershocks, or secondary tremors caused by the primary shock, typically continues for several weeks to months after major earthquakes. Although predicting the exact date of a more powerful event is impossible, seismologists constantly monitor the situation, controlling the development of regional seismic activity and changes in the stress field. Given the complex tectonics of the Caribbean Sea and South American plate boundaries, it can be confidently said that this region will continue to generate earthquakes in the future. However, the precise timing of large tremors remains unpredictable, highlighting the complexity and multifaceted nature of geophysical processes. The main goal of modern research remains an honest and objective presentation of multiple perspectives. A crucial aspect is the recognition of universally accepted scientific explanations based on verified physics and supported by an extensive system of observations. Speculative hypotheses, despite their appeal, must be approached with caution. In the past, during the era of our ancestors, people could observe bright flashes of newly forming stars and feel earthquakes caused by powerful geological processes within our planet. However, they could not understand that these natural phenomena were connected to more global and cosmic events, solar storms or the approach of interstellar objects, because the technology capable of recognizing such connections and analyzing them did not yet exist. Today, science teaches us to distinguish between what we observe directly and what we imagine, to separate facts from assumptions, and to understand the limits of human knowledge. We can differentiate proven facts, assess probabilities, and only hypothesize about possible scenarios. This raises the question: how can stars explode without being completely destroyed, leaving behind partial remnants? The answer lies in the physical laws operating on scales that often challenge our intuitive perception of the world. Thus, today we turn to the topic of 6, the anatomy of new stellar explosions, their internal structure, and the processes hidden behind bright flashes. Imagine a white dwarf, a compact stellar remnant roughly the size of Earth, yet containing the mass of our entire solar system. Its surface, under the influence of intense gravitational pull, compresses matter to such an extent that its density approaches that of 1,000 milliliters of water. That is, a state where atoms are squeezed into an extremely dense configuration. The surface temperature of this object reaches approximately 50,000 degrees Fahrenheit, making it extremely hot and luminous. Such a stellar corpse results from the death of a star similar to the Sun, which has exhausted its nuclear fuel, shed its outer layers, and subsequently collapsed into a sphere of degenerate matter. In this state, atoms exist under conditions different from those on Earth. Electrons and nuclei are in a compressed, dense state where traditional properties of matter change. Now, imagine this cosmic furnace, the white dwarf, located in close orbit with its stellar companion, such as a red giant. This giant is an aging star with an expanded outer shell, entering a stage of old age. The gravitational pull of the white dwarf gradually siphons hydrogen from the expanded atmosphere of the giant, like an invisible barrier pulling gas through interstellar space. This gas, spiraling inward, flows like water down a drain and accumulates on the surface of the white dwarf. Under the influence of gravity, this material becomes increasingly dense and hot, compressed under pressure created by the contraction. For decades, centuries, or even millennia, hydrogen continues to accumulate on the surface of a stellar remnant, forming a thick layer. Gradually, the temperature and pressure within this layer increase as additional material is compressed and heated more intensely. Unlike controlled nuclear fusion, which occurs in the cores of stars and is maintained by a stable balance between gravity and thermonuclear reactions, in such cases, hydrogen accumulation leads to an explosive event, a so-called thermonuclear explosion. When the temperature reaches approximately 100,000 million Kelvin, a reaction is triggered that results in an explosion. This explosion, a powerful event occurring in just a few seconds, releases an effect comparable to the energy output of 1,000 years of sunlight, unleashing enormous amounts of energy in a very short time. Unlike a typical supernova, where the entire star is completely destroyed, in this case, the white dwarf does not die entirely. It merely loses its surface layer, which is captured by the explosion. The rest of its core remains intact and continues to exist, ready for new cycles of accumulation and explosion. That is why high-energy signals, phenomena of high energy, observed in space often transform from simple brightness variations of stars into truly vast and astonishing events, akin to cosmic particle accelerators. Imagine an expanding shell of matter ejected from a star that has exploded, moving at several thousand kilometers per second. When this shell collides with the sparse interstellar gas, powerful shock waves are generated. These waves essentially function as natural cyclotrons, devices that use magnetic fields to accelerate charged particles. As a result, protons and electrons reach energy levels that require the operation of the largest and most expensive laboratories on Earth. In this sense, cosmic phenomena become analogues of super-powerful accelerators, creating conditions for research at levels inaccessible in our laboratories. In the context of studying such events, the cooperation of amateur astronomers plays a crucial role. The American Association of Variable Star Observers actively coordinates amateur participation in scientific research by implementing standardized photometry protocols, enabling the collection of comparable and precise data. While visual observers estimate the brightness of novae by comparing it to the brightness of known standard stars, CCD cameras, charge-coupled devices, provide high-precision measurements capable of detecting even the slightest changes in the light curve. These observations allow tracking the brightness dynamics of novae in real time, which is especially important for understanding their evolutionary processes. Thanks to hundreds of amateur observatories around the world, we are able to obtain temporal resolutions that large professional facilities, focused on multiple objectives simultaneously, cannot achieve. When it comes to the development of nova brightness, such as the 5 Centauri stars, their behavior strictly aligns with models developed over decades of research. Typically, the brightness growth process, from disappearance to reaching the peak, takes from several days to several weeks. The maximum brightness, or peak, can last from a few days to several months, depending on numerous factors: the white dwarf's mass, accretion rate, characteristics of its companion, and the composition of the ejected material. After reaching the peak, a decline phase follows, which can extend over months or even years. Sometimes, this decline is accompanied by secondary peaks, outbursts caused by various physical processes occurring within the system, indicating the complex and multifaceted nature of these events. Spectroscopy is a powerful tool in nova research, allowing scientists to determine their chemical composition and physical conditions. In the first days after the explosion, spectra display broad emission lines of hydrogen, helium, and heavier elements moving at high velocities. These broad lines serve as evidence of expanding material ejected from the star. As this material cools and slows down, the spectral lines gradually narrow and shift. In the final stages, so-called forbidden lines appear, transitions that are only possible under extremely low-density conditions characteristic of expanding shells. Atoms in such shells can remain collision-free for hours or days, creating a unique spectrum specific to this type of event. Determining precise distances to objects like V1935 Centauri and V79924 Sagittary remains a challenging task. It is assumed they are located at distances exceeding several thousand light-years. This means that the explosions we observed in September 2025 actually occurred thousands of years earlier, at a time when humanity was just beginning to master agricultural skills and establish the first permanent settlements. The light from these stellar explosions traveled through interstellar space for a much longer period than the history of human civilization, and only at a certain moment did it reach Earth, bearing witness to events long past. Thus, we are not merely observing a bright flare event but peering into a distant past, about which human astronomical science can only speculate regarding the scale and details. Amateur astronomers using binoculars or small telescopes can determine the brightness of novae by comparing them with neighboring stars whose brightness is well known and documented in astronomical catalogs. These specialists often rely on visual methods, comparing the brightness of the observed object with the brightness of nearby stars, which allows them to roughly determine the star magnitude of the new object. In more complex cases, when observers have modern equipment, photometers with photodetectors, equipped with special filters and cameras with digital image recording, they can obtain highly accurate quantitative brightness measurements. Such data become a valuable addition to the observations of professional astronomers, especially when it comes to long-term monitoring of variable objects. The designation of new stars in official astronomical catalogs is based on established traditions and administrative rules. In particular, the name V1935U assigned to this variable star indicates its continuous inclusion in variable star lists. The number following the letter V is the sequential number of the object, reflecting its latest addition to the variable star catalog, while the letter and the subsequent U serve for unique identification. In this case, this star is officially listed in the variable star catalog in the constellation Centaurus, one of the brightest and most noticeable constellations in the southern sky. The prefix V indicates that it is a variable star, meaning an object whose brightness changes over time for various reasons. This permanent designation, fixed for the object, completely replaces temporary or less formal names that might have been assigned during initial observations. Initially, the new object might have been named after the surname of the discoverer, the date of discovery, or a number in some catalog created within a large sky survey program. Unlike such temporary or internally used designations, the permanent code V1935U serves as a universally accepted and easily recognizable identifier of this variable object within the scientific community. The process of dust formation is one of the most fascinating aspects of the evolution of newly formed stars. When an explosion occurs, releasing energy and matter, in the first weeks or months afterward, some novae experience a sharp decrease in brightness, associated with the formation and condensation of dust particles in the cooling ejecta. These events, called dust dips, can reduce the nova's luminosity by several orders of stellar magnitude, as microscopic dust particles absorb and scatter radiation emanating from the stellar core. Gradually, the dust either disperses or is destroyed under the influence of radiation and energy flows emanating from the remaining part of the stellar remnant, making it possible once again to observe the stellar structure underlying this process. This cycle of dust formation and disappearance is an important stage in understanding the processes occurring inside nova systems. The energy costs associated with novae explosions, despite their significance, are considered quite modest when compared to the scale of human experience and our daily lives. Typically, the energy released in a single explosion is about 10,000 times greater than the energy our Sun emits in 1 year. This amount of energy could easily sustain humanity for billions of years if viewed from the perspective of current consumption levels. However, in absolute terms, this energy remains insignificant compared to the power released during supernova explosions, stellar events that can illuminate entire galaxies within weeks or months, overshadowing everything around them. Recurrent novae form a special category that complicates the simple picture of isolated explosions. In some white dwarf systems, eruptions occur that resemble novae, with a relatively predictable periodicity, every few decades in the most frequent, recurrent systems. As a result, such systems can experience multiple outbursts over time. In the modern era of astronomical research, the discovery of new stars not only sparks interest but also often prompts deep reflections on their origins. Among these objects, dwarf novae occupy a special place. Their appearance is usually not caused by large-scale thermonuclear explosions within the star, but rather by more subtle and unstable processes occurring in the accretion disks surrounding compact objects. These eruptions are characterized by unusual spectral features and smaller amplitudes, making them more challenging to recognize and classify. Unlike bright red novae, which are often associated with the merger of two stars or other major events, these dwarf explosions demonstrate more modest and diverse manifestations. They can appear across a wide range of colors and have timescales ranging from several days to several months, reflecting the variety of physical processes underlying them. Interestingly, it is sometimes possible to hypothesize the existence of stellar objects that do not fully fit into the conventional scenarios associated with thermonuclear explosions. Could there be something more exotic among the newly discovered stars? So-called unusual or even hypothetical phenomena that go beyond standard models? It is quite likely that some of these objects represent unique cases or complex combinations of physical processes that require further study and more precise interpretations. Modern astronomical observations, based on a broad spectrum of methods and instruments, confirm the traditional understanding of classical novae, their physical nature, and the mechanisms of their formation. However, the scientific community, being inclined towards continuous development and re-evaluation of existing theories, maintains a healthy skepticism regarding initial classifications. Each new data collection, especially when utilizing multi-wavelength observations, allows for the detection of subtle details and nuances in the behavior of these objects, contributing to a more accurate determination of their physical characteristics. In recent years, particular attention has been drawn to the detection of gamma radiation emanating from specific new stars, such as V1935 Centauri. This event has challenged scientists to reconsider existing models, as gamma radiation is a manifestation of highly energetic processes. In the case of V1935 Centauri, it indicates that mechanisms for particle acceleration are occurring within these systems, operating much more efficiently than previously assumed. Such observations compel us to revise our understanding of the physical conditions inside new stars and the processes accompanying their explosions. It can be hypothesized that these mechanisms involve magnetic field reconnection, fast shock waves, or other complex physical phenomena capable of creating conditions for such intense energy emissions. These discoveries also open the possibility of a link between classical stellar explosions and more powerful astronomical phenomena, such as supernova remnants, significantly broadening our understanding of stellar cataclysms. While astronomers continue to observe and analyze these explosions across the electromagnetic spectrum, efforts are underway on Earth to demonstrate the internal dynamics of our planet. Despite the apparent stability of the Earth's surface, its interior space proves to be quite active and dynamic, ready for sudden shifts and shocks. These processes, as complex and diverse as stellar explosions, demonstrate that nature never ceases to surprise us with its hidden dynamism. In this context, there is interest in understanding how earthquakes occurring within our planet are related to geological features and the stresses accumulated over decades. Let us now examine in more detail one of the most complex and mysterious regions of the Earth's crust, namely the area beneath Lake Maracaibo and the surrounding lands of Zulia State in Venezuela. This region is indeed one of the most tectonically active and intricate in South America. Its unique geological structure is caused by the interaction of the Caribbean and South American plates, which have been in contact for a long time. Following powerful seismic events, secondary waves are generated that create transverse ground movement and often cause the greatest damage to structures, destroying buildings and infrastructure in the most severe manner. These secondary waves propagate more slowly across the planet's surface but often carry significant destructive energy, manifesting as swaying and vibrating motions of the Earth. Witnesses of such earthquakes describe these oscillations as prolonged, sometimes lasting several minutes in certain areas, creating a sensation of endless swaying and instability. The first of these strong tremors occurred at a specific time, 5.5 hours later, that is, at 3:50 Coordinated Universal Time on September 25. Subsequently, nearly in the same region, another major fault rupture took place, causing a second significant earthquake. Its magnitude reached 6.3, which was slightly stronger than the first event, and it occurred at a depth of 14 kilometers, much deeper than the previous rupture. However, even at this depth, considering its relative shallowness, the earthquake caused powerful surface oscillations and intense shaking. Most likely, this second event occurred on an adjacent fault segment that was under stress caused by the initial rupture. Understanding the physics of stress transfer mechanisms within the Earth's crust helps explain why earthquakes often occur in groups. A sudden displacement of one fault segment induces changes in the stress field on neighboring sections. In some areas, this stress increases, making them more vulnerable to potential future ruptures. In others, it decreases, temporarily reducing their susceptibility to seismic shocks. In the case of the rupture that occurred on September 24, an increase in stress was recorded precisely on the fault segment that, 15 hours later, at 3:50 Coordinated Universal Time, broke apart. Although the difference in magnitudes between the first and second earthquakes, 6.2 and 6.3, may seem insignificant, it is important to remember that magnitude is a logarithmic scale. This means that an increase of one whole unit in magnitude corresponds to roughly twice the amount of energy released. In this instance, the second earthquake released approximately twice as much energy as the first, and collectively, both events released energy equivalent to a single earthquake of magnitude 6.4. Such energy release is considered highly significant and ranks among the largest seismic events globally that occurred at the end of September this year. International seismological agencies reported several variations in the magnitude estimates of these earthquakes, which is related to differences in measurement and analysis methods. The United States Geological Survey uses the so-called moment magnitude, a measure based on the total energy released during the rupture. Meanwhile, the European Mediterranean Seismological Center may employ different magnitude scales, based either on the amplitudes of surface waves or on the characteristics of volumetric waves within the Earth's crust. These methodological differences, as well as the continuous updating of data as new results from various seismographs become available, explain why news headlines and reports feature magnitude estimates ranging from 6.1 to 6.3. The sequence of subsequent shocks, aftershocks, followed certain patterns that seismologists have observed and documented over many decades. In particular, the earthquake with a magnitude of 5.8 that occurred after September 25 is a classic example of what is known as a strong aftershock. Such shocks are usually less powerful. The effects of recent earthquakes have been felt not only in neighboring countries such as Venezuela but also across Colombian territory. Their impact was widespread because the epicenters of these seismic events were located at relatively shallow depths beneath the Earth's surface. This proximity to the surface significantly amplified the amplitude of ground vibrations, which necessitated the urgent organization of evacuations from high-rise buildings in the region's largest cities. At that time, social media was flooded with videos capturing dramatic scenes: lamps swaying in sync with the earthquake, windows rattling under the tremors, and people rushing to leave their homes and offices, fearing possible aftershocks. In response to the regional events, emergency response protocols were activated, helping to organize rescue efforts and ensure public safety amid unpredictable seismic activity. Although initial reports of extensive destruction and casualties remained relatively sparse, it is important to note that the earthquake's magnitudes were high enough that, over the following days, regional damage assessment teams systematically documented both visible damage to buildings and infrastructure and signs of potential long-term structural weakening. This process allowed specialists to understand the scale and potential consequences of the events, as well as to prepare recovery and reinforcement measures for the affected structures. The causes of such powerful earthquakes are rooted in regional geology. The Maracaibo Basin, where these events occurred, was formed as a result of complex and multifaceted tectonic processes associated with the interaction of two major lithospheric plates, the Caribbean Plate and the South American Plate. These plates, moving relative to each other, have created a network of fault systems and zones of stress that regulate the tectonic activity of the region. Within this basin lies Lake Maracaibo, situated in a graben, a depressed block of the Earth's crust bounded by normal faults, that continues to experience active deformation and movement as part of ongoing geological processes. It is precisely these geological features that make the region particularly susceptible to strong earthquakes. Additionally, this area is home to rich oil fields, which are a vital component of the region's economy. They formed in sedimentary basins created by the same tectonic movements that cause earthquakes. This means that geological activity simultaneously generates valuable resources and poses risks to infrastructure. At the same time, measurements of earthquake focal depths are highly uncertain, especially in such complex geological conditions. For the first event, with a magnitude of 7, and the second, with a magnitude of 14 kilometers, approximate estimates were made based on the arrival times of seismic waves at several observation stations. These estimates indicate that both earthquakes occurred in the upper part of the Earth's crust, where brittle fracture and failure are characteristic of this layer, unlike the deeper zones where increasing temperature and pressure lead to ductile deformation. questions arise regarding potential factors that could trigger such powerful seismic events. Specifically, there is interest in whether external influences, such as solar activity, changes in atmospheric pressure, or other natural factors, could affect earthquake occurrence. The scientific consensus, supported by experts and institutions such as the United States Geological Survey and international organizations, states that there is no reliable evidence linking space weather to seismic activity. Decades of statistical research have failed to reveal significant correlations between solar flares, coronal mass ejections, geomagnetic storms, and earthquakes. However, some scientists have explored more subtle and delicate possible connections. For example, changes in atmospheric pressure may exert a minor influence on stress levels in faults. The database known as the Global Centroid Moment Tensor provides a crucial source of information, offering detailed analysis of earthquake characteristics. It reveals parameters such as fault orientation, slip directions, and rupture mechanisms for each recorded event. In the case of 2 recent earthquakes in Venezuela, this data was particularly valuable. It is presented in the form of diagrams resembling swords, or what are also called beach sword diagrams, which help seismologists understand the specific planes along which faults ruptured and the directions of Earth mass movements. This information plays a key role in understanding regional stress fields and serves as a basis for forecasting potential areas at increased risk of future earthquakes. Such analytical methods enable us to determine where the probability of upcoming strong tremors is highest, and where, conversely, the risk remains minimal. Modern statistical seismology is currently the only reliable and systematic approach to earthquake prediction. In conditions where the nature of these phenomena remains largely unpredictable, analyzing statistical data allows us to at least estimate the likelihood of new tremors occurring. After powerful earthquakes, such as those recently shaking the Venezuelan lands, the region experiences a temporary increased risk of subsequent strong underground shocks. This is related to the activation of stress transfer processes and re-sliding along faults during such periods, as well as the fact that recent tremors can induce additional shear movements in adjacent sections of the Earth's crust. However, it is important to emphasize that this heightened risk cannot be predicted with certainty. It exists only as probabilistic estimates and typically persists for several weeks or months after the main earthquake. During this period, it is impossible to determine the exact moment or specific location where the next powerful tremor will occur. In regions with high seismic activity, such as the Zulia state, specialized systems are being developed to protect lives and property. Continuous inspections, improvements in building codes, and rapid response systems for emergencies help minimize earthquake consequences. For example, even during earthquakes with magnitudes of 6.5, reports of destruction are often moderate. This indicates both timely reactions and coordinated actions by emergency services, as well as ongoing improvements in regulations governing construction. Modern building standards require that structures be designed to withstand strong ground vibrations, significantly reducing the risk of collapses and damage. However, despite these measures, many old buildings remain vulnerable because they do not meet modern standards and may suffer or be completely destroyed during strong tremors. A logical question arises: can more powerful earthquakes occur in the same region? Geologically, this possibility is certainly plausible. For example, around Lake Maracaibo, earthquakes with magnitudes of 7 and above have repeatedly occurred throughout history, driven by fault systems associated with regional tectonics. Regional tectonics, meaning the movement of lithospheric plates, suggests that such strong shocks will happen irregularly over geological time. Nevertheless, seismologists are currently unable to predict precisely when the next major fault rupture will occur, whether in days, years, or even decades. The only thing that can be stated with certainty is that the probability of their occurrence exists and remains high, especially in areas with active faults and complex geological conditions. Overall, the study of the earthquake sequence in Venezuela shows how powerful Earth processes can cause significant energy releases, which, despite their scale, are quite understandable from the perspective of the physical laws operating over geological timescales. Stress accumulation in the Earth's crust occurs slowly, as tectonic plates move relative to each other at a rate of only a few centimeters per year. When this stress reaches a critical point, and the indices of solar activity in recent months painted a rather vivid and intense picture for scientists and solar physicists, with the Sun functioning almost at the peak of its possible activity. One of the key indicators used to assess the level of activity of our star is the level of radio emission at a specific frequency, 10⁻⁷ centimeters. This measure, recorded daily by amateur and scientific observatories, fluctuated at the end of September between approximately 180 and 190 solar units. These daily measurements, obtained through modern radio observatories, demonstrate a close correlation with the number and size of active regions forming on the Sun's surface. When this indicator exceeds 150, it is generally considered a sign of increased solar activity, and if it reaches 200 or higher, it indicates extremely active conditions capable of triggering serious space phenomena, affecting space weather as well as satellites and Earth's electronics. In this measurement system, sunspots, dark, noticeable areas on the star's surface that tell stories of magnetic storms raging inside the photosphere, hold particular significance. These regions, often larger than the area of our planet, form where very strong magnetic field lines penetrate through the solar layer, suppressing normal convection processes necessary for heat exchange. In the cores of sunspots, magnetic fields can reach strengths of over 3,000 Gauss, roughly 6,000 times stronger than the magnetic field observed on Earth's surface. The more such spots appear on the solar disk, the higher the likelihood that within them, intense twisting of magnetic lines occurs, leading to reconnection and the accumulation of enormous amounts of energy that can suddenly be released as solar flares or powerful coronal mass ejections. However, only dry numbers regarding the number of spots provide a very approximate understanding of the complex dynamics of the solar maximum. The Sun's magnetic field during periods of high activity resembles a tangled, twisted network rather than the relatively simple dipolar field characteristic of solar minima. In active regions where sunspots are concentrated and connected by numerous magnetic loops, these structures can persist for weeks or even months, rotating with the Sun across its surface. From time to time, such regions produce powerful eruptions observable by spacecraft located within the solar system. Among the most dramatic manifestations of solar activity are coronal mass ejections, or CMEs, events in which the magnetic lines in the Sun's corona become so twisted and stressed that they suddenly break apart and reconnect. This process converts the accumulated magnetic energy into kinetic energy of charged particles, which are immediately ejected into space. As a result, a powerful plasma flow with a mass of billions of tons is generated, traveling at speeds ranging from about 250 km per second in the slowest events to over 3,000 km per second in the fastest eruptions. To monitor and predict such solar storms, scientists use specialized models, among which the WSANL model developed by the Space Weather Forecasting Center stands out. This complex computer system creates a three-dimensional simulation of the propagation of coronal mass ejections, dividing space into a grid extending from the solar disk to Earth's orbit. The model calculates how parameters such as solar wind, plasma density, and magnetic field orientation change as the energetic clouds, containing billions of tons, move through the solar system. Although this model accurately predicts the arrival time and intensity of CMEs, it cannot capture all the subtle details of their internal structure and behavior. Overall, forecasting solar activity and its impact on space weather is an extremely complex task that requires a combination of precise measurements and advanced computer models. The autumnal equinox traditionally amplifies the effects of these cosmic phenomena due to the so-called McFarlane effect. This interaction is geometric in nature, driven by the orientation of the magnetic field emanating from our planet and interacting with the interplanetary magnetic field carried by the solar wind. It is during the equinox periods that this geometric configuration becomes particularly favorable for magnetic reconnection between magnetic structures originating from the Sun and Earth. Such magnetic reconnection occurring at this time often causes strong geomagnetic disturbances, or, in other words, geomagnetic storms, even if solar activity at that moment is moderate. The impact of space weather exceeds the conventional understanding of the auroras, which undoubtedly attract public attention, as geomagnetic disturbances can significantly affect numerous technological systems. In particular, such storms can disrupt high-frequency radio communications, widely used in aviation and maritime navigation, causing outages and reduced signal quality. They also require satellite operators to perform constant orbital adjustments, since increased atmospheric drag due to the expansion of the upper atmosphere during active solar events can alter spacecraft trajectories. In more extreme cases, geomagnetic storms can threaten the stability of Earth's power grids by inducing electric currents capable of damaging transformers and other electrical infrastructure. To assess the level of danger and enable timely responses to these processes, the scientific community uses specialized scales developed for classifying the strength of geomagnetic storms. These include the Solar Radiation Storm Scale, the Magnetic Activity Scale, and the Radio Blackout Scale, each helping various industries and scientific fields prepare for potential space weather consequences. With these tools, specialists can more accurately forecast and minimize damage related to magnetic disturbances. Phenomena associated with coronal mass ejections and their interactions with comets create unique natural laboratories for studying plasma physics under conditions impossible to replicate on Earth. Comet ion tails form when the solar wind strips electrons from gas molecules in their comas, resulting in charged particles moving along magnetic field lines directly emanating from the Sun. These tails can extend millions of kilometers, serving as vivid evidence of invisible magnetic processes occurring within our solar system. The interaction becomes particularly dramatic and spectacular when coronal mass ejections, CMEs, collide with comets. In 2007, the European Space Agency documented such an event with the Stereo spacecraft. During this event, the ion tail of the Encke comet completely detached due to magnetic reconnection triggered by the powerful CME. The detached tail quickly drifted away over several hours, while a new tail formed from fresh material, clearly demonstrating the high dynamics of this interaction. These observations vividly illustrate how variable and complex space weather is, and how it influences objects within our solar system. Regarding solar activity, the year 2025 proved to be filled with active events that create an intense background for space operations, such as the Atlas mission approaching the inner solar system. Unlike previous interstellar visitors, which passed by our Sun during periods of relative solar cycle calm, the new object encountered conditions of high solar activity. This resulted in space weather phenomena with high intensity, increasing the likelihood of significant interactions. It is particularly noteworthy that the frequency of coronal mass ejections, CMEs, during this period was noticeably elevated, and the object's trajectory crossed the ecliptic plane, the region of the solar system where most active solar processes are concentrated. All of this greatly heightened the chances of collisions and interactions capable of affecting spacecraft operations. Several solar coronal mass ejections can interact with each other, merging into larger and more powerful disturbances, and sometimes creating complex magnetic configurations that substantially enhance particle acceleration processes and magnetic reconnection. Such interactions on the Sun often lead to increased solar activity and more complex conditions within the solar system, which, in turn, significantly influence space weather near Earth. Professional space weather forecasters utilize numerous data sources, continuously monitoring solar activity and attempting to predict potential impacts on our planet. In particular, the Solar Dynamics Observatory provides continuous monitoring of the Sun's surface and corona through high-quality images obtained at various extreme ultraviolet wavelengths, helping to detect even the smallest changes and early signs of upcoming events. By observing solar activity, specialists also rely on data from the Solar and Heliospheric Observatory, SOHO, which tracks coronal mass ejections erupting from the far side of the Sun, inaccessible to conventional observation stations. Additionally, the Advanced Composition Explorer (ACE) spacecraft, positioned at the Lagrange point between Earth and the Sun, offers crucial early warnings of approaching solar winds and related magnetic disturbances, enabling timely alerts about space origin threats. An important component of space weather monitoring is contributed by radio amateurs, who form an informal global network of observers helping to track the influence of solar activity on Earth's communications. During geomagnetic storms, changes in the propagation of radio waves in the high-frequency range become particularly noticeable. Sometimes they enhance communication over long distances due to reflection of radio waves in the ionosphere, while at other times they degrade signal quality because of increased absorption and scattering of radio waves. These observations, obtained by amateurs, complement official data from professional stations and help form a more complete understanding of the state of the space environment. Regarding the current solar maximum, it appears to follow a two-peaked model, which has been observed in some previous solar activity cycles. The first peak is expected in the early 2020s, around the 20s of the current century, and after that, activity should remain high throughout the following, the 25th year. This prolonged maximum phase indicates that risks associated with space weather could persist significantly longer than typical for 11-year solar cycles. This means that conditions capable of causing strong solar-terrestrial interactions may last until 2026, requiring special attention from specialists and users of technology sensitive to the space environment. During this solar maximum, observing the polar lights has become an especially popular activity among amateur astronomers and professional researchers. Social media has been flooded with bright and captivating images of green, red, and violet lights dancing across the sky in polar and subpolar regions of the planet. These auroras occur as a result of charged particles ejected from solar storms interacting with Earth's upper atmosphere. The excitation of oxygen and nitrogen atoms leads to their return to the ground state, accompanied by the emission of characteristic colors, creating the effect of bright auroras. The solar wind, propagating through the solar system, carries embedded magnetic fields generated in the sun's corona. These magnetic fields, like threads stretched between various objects in space, form interplanetary magnetic field lines connecting planets, comets, and spacecraft into a vast network of electromagnetic interactions. These lines extend far beyond Earth's orbit, reaching the boundary of the heliosphere, the region where solar pressure balances with the interstellar medium. Early morning light on July 1, 2025, at the hour when night darkness had not yet given way to the first light of dawn, recorded an unusual movement against the backdrop of silent star points on the Asteroid Impact Monitoring System, or ATLAS for short. At that moment, when most observers were still waking up, the telescopic setup detected a faint, barely noticeable movement that initially seemed like a random burst of light or perhaps a cometary object. However, thanks to rapid and precise orbital modeling, scientists were able to determine that what they faced was not just another celestial object within the solar system, but something far more mysterious and unique. This object was designated TriAI Atlas, indicating its status as the third confirmed interstellar visitor, after the enigmatic Oumuamua, discovered in 2017, and comet Borisov, observed in 2019. The name, TriAI Atlas, not only signifies its sequential position among interstellar visitors but also references the telescope system that first detected its hostile yet simultaneously captivating movement along an interstellar trajectory. The designation, 3I, is the official prefix assigned by the International Astronomical Union, confirming this object as the third interstellar body recognized by humanity. At the same time, the word Atlas pays homage to the system that first recorded its appearance, a symbol of hope and scientific progress in the exploration of space. Unlike its predecessors, which appeared unexpectedly in our view and with limited capabilities for detailed study, TriAI Atlas arrived during a unique observation window when its brightness reached a level suitable for comprehensive analysis. Its trajectory passed close to the ecliptic, the plane where most planets and small bodies of the solar system are concentrated. At the peak of solar activity, the so-called solar maximum, incredible opportunities arose to observe how solar activity influences the interstellar material passing through our system. Regarding the orbital characteristics of this cosmic wanderer, they can truly be called astonishing and indicative of its extraterrestrial origin. Its trajectory was hyperbolic, with an eccentricity significantly exceeding 1, indicating its high velocity sufficient to escape the Sun's gravitational pull. In simpler terms, it is moving so rapidly that, upon reaching a certain point, it can easily leave the boundaries of the solar system and venture into interstellar space without returning. The orbital inclination, approximately 95 degrees, means that TriAI moves in a retrograde direction relative to most planets, i.e., it moves backward compared to their usual orbital motion. Currently, scientists estimate that the size of this object is at least several hundred meters, and according to the most optimistic estimates, its diameter could reach 15 kilometers, although these figures remain quite tentative due to limited data. Visual images obtained even with the largest ground-based telescopes show only a blurred light surrounded by faint gas and dust coma. This faint point of light does not allow for precise determination of the object's size or structure. All estimates of its dimensions are based on assumptions about its reflectivity and composition, as well as the level of activity, which can vary greatly. In the case of an interstellar object formed around a foreign star, such parameters remain largely uncertain. A particularly significant date in astronomical science is October 3, 2025, when its closest approach to our planet is expected. On this day, when TriAI Atlas will pass at a distance of approximately 0.19 astronomical units from Mars, it will be roughly 20 times closer than its previous observations. Although this resolution does not allow for detailed surface features of the visitor's core to be seen, it still provides valuable information about its structure. Specifically, it can distinguish a compact central cluster concentrated in its core from a more diffuse, blurred cometary envelope surrounding the core. These observations hold scientific value beyond mere imaging. During the flyby past Mars, spectroscopic measurements taken at that moment could reveal the chemical composition of the gas escaping from the core of the visitor. Such release occurs under the influence of solar heat, which heats and activates ancient volatile compounds hidden inside the comet. Spectra are expected to show lines corresponding to molecules such as cyanogen, CN, carbon dioxide, and carbon monoxide, CO, helping to understand the chemical nature of this object. These spectral data can provide important clues about the material from which the star system, in which the visitor originated, was formed, and about the physical conditions that existed in its early epochs. However, such spectroscopic observations will not provide direct confirmation of the exact chemical composition of the core, but they are very important for understanding its origin and evolution. The entire world, from professional astronomers to amateurs, actively participated in observing this unique object throughout its approach. Particularly significant were the initial reports that the brightness of the visitor increased faster than initially expected. This unexpected fact prompted additional research and analysis, as the light curves require careful calibration and verification to confirm their accuracy. The southern hemisphere's sky favors observers in that region, as the visitor is located in the southern part of the sky, making it easily accessible to amateur and professional astronomers in southern latitudes. At the same time, observers in northern latitudes can track the object early in the morning when it rises above the southern horizon. For more precise and systematic monitoring, major astronomical organizations continue their collaboration, such as the American Association of Variable Star Observers and the Minor Planet Center. Their efforts are focused on studying brightness variations, the morphology of the tail, as well as the spectroscopic evolution of the visitor as it responds to increasing solar heat during its approach to the Sun. The trajectory of this object through the inner regions of the solar system provides numerous opportunities for extended observations, which are planned to be carried out until the beginning of the year 2026. After passing by Mars, the visitor, named TRIGO October TriAI Atlas, will continue its journey toward perihelion, its closest point to the Sun, which is scheduled for October 29. At that moment, it will be approximately 14 astronomical units from the Sun. This distance allows it to remain beyond Earth's orbit, yet still within reach of modern ground-based telescopes and orbital observatories. In late 2025 and early 2026, it will come closest to our planet, passing at a distance of about 1/8 of an astronomical unit, or roughly 270 million kilometers. For comparison, this distance is less than the farthest position of Mars relative to Earth, creating excellent conditions for observations by both professional and amateur astronomers equipped with small telescopes. During this period, when the visitor is near perihelion, scientists will be able to determine whether its behavior aligns with typical comet evolution models or if it possesses unique characteristics indicating an interstellar origin. Solar radiation acting on the object can release volatile compounds that have remained frozen inside it for millions of years as it traveled through interstellar space. This activation process can cause a sudden increase in brightness, the formation of a bright tail, or other characteristic phenomena. In professional photographs capturing the comet, ion structures are clearly visible, directed strictly against the solar light, consistent with the classical behavior of comet tails. These ion tails generally extend straight back along the trajectory, opposite to the direction of solar radiation, due to the influence of the solar wind on charged particles in the coma. However, some amateur observers, based on their own observations, report the presence of field structures that seemingly point forward, in the direction of the comet's movement, which appears to challenge conventional comet physics. These seemingly contradictory reports most likely reflect differences in the physical mechanisms forming various types of tails rather than indicating any unusual or exotic phenomena. In particular, dust or plasma tails are formed under the influence of solar radiation pressure, that is, a gentle but continuous force exerted by sunlight on tiny particles released from the comet's nucleus. These particles, responding to the combined effects of radiation pressure and gravity, move along curved trajectories, creating elegant, curved tails that we observe in most comet photographs. Depending on the viewing geometry and the observer's position relative to the orbital plane, such plasma tails can appear to be oriented in different directions, sometimes even opposite to each other, which complicates their interpretation. At the same time, ion or gas tails are formed through a completely different physical process. Here, the solar wind, a stream of highly energetic charged particles, mainly electrons and ions, strips electrons from gas molecules in the coma, creating charged particles that interact with magnetic field lines embedded in the solar wind. These particles, moving along magnetic field lines, are directed straight away from the sun, forming narrow, straight tails that change direction depending on the orientation of the magnetic field and variations in solar wind conditions. As a result, ion tails can appear as long, straight filamentary structures that constantly shift in direction and shape, reflecting the dynamics of magnetic fields and solar activity. Regarding the estimation of the size and composition of a comet, especially objects like TriATLAS, there are fundamental challenges inherent in interplanetary research. Even the most advanced and powerful telescopes are unable to resolve surface details of objects smaller than large asteroids at distances exceeding several astronomical units. This is due to limitations in the resolving power of instruments and the fact that the farther the object, the less accurately its size and structure can be determined. Typically, size estimates are based on brightness measurements, assumptions about the surface's reflectivity, and models that estimate how much light the object scatters toward Earth. Some sources have speculated that TriATLAS could have a diameter of up to 15 miles. However, such estimates require cautious interpretation because they are based on indirect data. More accurate conclusions require the use of thermophysical models that combine brightness measurements with infrared observations of thermal emission, helping to determine the actual size and composition of the object. An important factor is also the comet's activity level, the amount of gas and dust it ejects, which directly influences its brightness and, consequently, the interpretation of its size. The more radiation and particles the object emits, the more difficult it becomes to precisely determine its true scale. The coincidence of this object's approach to Earth with another bright celestial event promises to make October 25th of our calendar year an especially memorable month for astronomy enthusiasts and night sky observers. During this period, not only is there planned observation of the approaching comet, but also the possibility to witness another impressive celestial phenomenon, which in scale and effects could overshadow all previous events. All of this creates a unique atmosphere of anticipation and wonder, as such events do not happen very often. The comet, designated C25R2, was first discovered thanks to data obtained from the Solar and Geophysical Observatory SOHO-SWAN, and has become the focus of close attention from amateur and professional astronomers worldwide. particularly notable was the contribution of citizen scientists, among whom Vladimir Bezugly is distinguished. On September 11 and 12, he observed an unusual luminous object in his observations, which appeared for the first time in data from the Solar Geophysical Observatory. This observatory continuously monitors the solar corona and surrounding space environment using specialized instruments, including the SWN device, designed to study the anisotropy of the solar wind. It allows for creating hydrogen emission maps across the entire heliosphere and periodically detecting the passage of comets as they begin to brighten and emit gases as they approach the inner solar system. Thanks to such systematic monitoring, Vladimir Bezugly noticed a brightening object that did not match any known comets or asteroids at that time. His careful analysis of numerous images confirmed that it was indeed a new cometary object. Preliminary orbital calculations indicated that this was a long-period comet, most likely making its first recorded approach to the inner planets of the solar system, a unique event in the history of astronomy. It is important to note that Comet Swan reached perihelion, its closest point to the Sun, on September 12, 2025. This moment occurred just a few days after its discovery, which largely explains the sharp increase in brightness recorded by Vladimir Bezugly. Typically, comets brighten most dramatically when approaching perihelion, as solar heat begins to intensely release volatile substances from their nuclei. This process results in the formation of characteristic comet structures, a bright nucleus, tails, and gas streams, which become clearly visible from Earth. Regarding observational conditions, the orbital geometry in October 2025 favors good visibility of the comet from both hemispheres of the planet. However, initially, more favorable observing conditions prevailed for southern observers, since the comet's position was more advantageous for southern latitudes. Gradually, as October progressed, the situation changed. The relative position of the comet to Earth and the Sun improved for observers in northern latitudes, opening up additional opportunities for amateur astronomers, professional astronomers, and simply anyone who enjoys observing the night sky. According to current forecasts, the brightness of Comet Swan, which will reach its closest approach to Earth, may vary between 4 and 6 stellar magnitudes. This means it will become sufficiently bright to be easily visible to the naked eye in dark skies without the need for optical devices. However, having binoculars or a small telescope will significantly enhance observing capabilities, allowing one to discern finer details of the comet's structure, its tails, and gas streams. It should be emphasized that brightness estimates for the comet come with considerable uncertainty, as the behavior of new comets, especially those making their first approach to the inner solar system, is often highly unpredictable. They can shine brightly or, conversely, remain less noticeable, depending on numerous factors such as nucleus composition, approach speed, and the presence or absence of active regions. That is why the upcoming late October 2025 becomes particularly important for astronomers and enthusiasts. During this period, around the 20th and 21 stone, the Moon will be in the new phase, meaning the night sky will be at its darkest, greatly facilitating the observation of faint objects, including the comet. On these same nights, the annual peak of the Arietid meteor shower activity occurs, which is formed from fragments of Halley's Comet crossing Earth's orbit. The coincidence of these events creates a unique opportunity to observe both the comet and meteorites simultaneously. Astronomy enthusiasts, passionate about observing the night sky, will have a rare chance in the coming months to witness a bright comet appearance accompanied by numerous meteor streams per hour and the ongoing evolution of the comet under the same favorable observing conditions. These phenomena promise to be spectacular and memorable, allowing not only amateurs but also professionals to record important features of cosmic objects in real time. It is especially interesting that the status of the comet named S, which is part of the solar system with a long orbital period, sharply differs from that of the interstellar object designated as 3IATL. Although both of these celestial bodies likely contain similar volatile compounds, such as water ice, carbon monoxide, carbon dioxide, and various organic molecules, they formed in entirely different environments and under different conditions, making their study particularly valuable for understanding the processes of formation and evolution of cosmic objects. Comet S was formed from materials located in the outer regions of our solar system approximately 4.5 billion years ago. It is possible that it spent most of its existence in the distant Oort cloud, a giant spherical cluster of icy bodies and cosmic debris surrounding our system. Then, under the influence of gravitational disturbances from other stars or internal forces, this comet was directed toward the Sun, leading to its first, and possibly only, approach to our star during its long life. Consequently, the scientific questions related to each of these objects differ significantly. In the case of the comet named 3IATL, we gain valuable insights into the processes of star system formation, interstellar chemistry, and how cosmic radiation affects materials traveling through interstellar space for millions of years. These findings help us understand how star and planet systems form and evolve, as well as how interstellar materials are influenced by solar and cosmic radiation. While Comet S, as an object within our solar system, provides unique information about the conditions that existed during the early epoch of the Sun's formation and its protoplanetary cloud, as well as about the composition and structure of the Oort cloud, Comet 3IATL helps us understand processes occurring beyond the solar system. Particularly important is how solar heat affects pristine cometary materials when the comet first approaches the Sun. This knowledge allows astronomers and enthusiasts to better understand how the composition and structure of cometary bodies change under the influence of solar heating, and how these changes are reflected in their appearance and behavior. In October of this year, we are set to witness a double cometary apparition, an event that will attract the attention of both professional and amateur astronomers. During this period, numerous opportunities will arise for photographing and documenting the observed objects. Wide-angle cameras, capable of capturing both comets simultaneously in a single frame, are widely used for this purpose. This approach will allow us to record their relative positions in the sky, compare their brightness, and analyze the structural features of their tails, significantly enriching our understanding of each of these cosmic objects. By capturing images at regular intervals, it becomes possible to observe dynamic changes in the morphology of the comet's coma, as well as in the orientation and length of its tails. These changes occur under the influence of variations in solar wind and shifting distances between Earth and the Sun. Such observations are crucial for understanding the processes occurring within comets and help identify patterns in their evolution. However, it is important to note that the brightness evolution of comets is often unpredictable, and forecasts in this area frequently face uncertainties. Some comets can significantly exceed expectations, increasing in brightness and developing impressive, luminous tails that reach such lengths they become easily visible to the naked eye, even amid urban light pollution. These bright comets can become true stellar objects. Events related to disconnections, when intense coronal mass ejections detach ion tails from comet nuclei, are rare but highly significant moments in the study of space weather. These phenomena can be observed in real time using modern telescopes, providing a unique opportunity to record the dynamics of processes occurring in space at the moment they happen. Such experiences help scientists and amateur astronomers better understand the physics of solar-wind interactions with comets, as well as the behavior of their tails during strong solar disturbances. Almost all amateur astronomers employ various methods to track changes in comet brightness and morphological structure. Visual estimates of magnitude are based on comparing the comet's brightness with that of nearby stars known for their stability. This method provides valuable data about the comet's condition, despite the fact that professional observatories generally cannot ensure continuous monitoring due to resource and time constraints. At the same time, photographic methods, including digital cameras and systems with flat-panel charged-coupled devices, CCDs, significantly improve measurement accuracy. These systems not only allow precise recording of brightness variations but also document structural transformations within the coma and tail, which is very important for understanding the dynamics of cometary formations. The question of a potential collision between Earth and debris from Comet Swift-Tuttle attracts heightened interest and some speculation within scientific and amateur circles. If our planet's orbit indeed intersects with the trail left by this comet during its previous passages through the inner solar system, we could witness a meteor shower. In such a case, particles left behind by the comet would enter Earth's atmosphere, producing bright meteors visible to the naked eye. However, such events remain quite unpredictable, especially when it comes to recently discovered comets, for which the details of their orbits and disintegration traces are not yet well understood. From time to time, spectroscopic observations of both comets in October can provide valuable insights into their chemical composition, revealing similarities and differences in their chemical fingerprints, which can shed light on their formation history and origin. The use of spectrometers in professional observatories allows for the detection of characteristic emission lines from various molecules, such as carbon monoxide, C-cyclohexane, C2, hydroxyl groups, O, and amines, nitrogen dihydride. These lines indicate which volatile compounds subliminate from the comet nuclei under the influence of solar heat. Analyzing such chemical fingerprints enables determination of the nucleus composition, understanding of its formation conditions, and tracking of the comet's evolution over time. When preparing to observe the double comet in October, selecting the observation site becomes particularly important. Ideal locations are those with minimal light pollution, dark nights, clear skies, and an unobstructed horizon free from artificial lighting. In urban environments, where light pollution significantly reduces the clarity and visibility of faint objects, comet observation becomes much more difficult. Therefore, to obtain the highest quality data, it is recommended to choose rural or remote areas away from city infrastructure, where the air is clean and the atmosphere is calm. Weather conditions at the end of October can vary greatly depending on the observer's geographic location. Some regions may experience clear, cloudless weather, while others might have fog, clouds, or precipitation, requiring flexible planning and readiness to postpone observations. For casual observers without professional equipment, binoculars often prove to be more convenient and effective than telescopes. Thanks to their wide field of view, they allow for a complete view of a bright comet, its nucleus, the dispersed coma, and the tail in a general context, without losing the overall impression. Models of binoculars with magnifications of 7 or 10 times, as well as sufficiently bright optics, such as 7 or 10-fold zooms, provide good light sensitivity without causing fatigue. Observing celestial objects and phenomena is an exciting and very important activity carried out with a variety of equipment located around the world. Professional astronomical observatories from different countries actively collaborate, combining efforts to conduct observational campaigns aimed at studying various cosmic bodies and phenomena. Such coordinated efforts ensure the most comprehensive and thorough coverage of observations, spanning a wide range of electromagnetic wavelengths. For example, the Hubble Space Telescope is capable of capturing images with very high resolution, allowing us to see the tiniest structural details on the surface or in the vicinity of celestial objects, details that are impossible to obtain with ground-based observatories due to atmospheric interference and optical limitations. At the same time, radio telescopes located on Earth play a crucial role in detecting molecular emission lines, which enable scientists to determine the chemical composition and thermal characteristics of expanding cometary clouds. They also help in understanding the processes of their evolution and interaction with the environment. Safety concerns when observing comets are generally considered minimal, especially when compared to more complex and potentially hazardous astronomical events such as solar or lunar eclipses. Comets typically do not pose a direct threat to observers and usually do not require special protective filters or equipment, except in certain situations related to specific observational conditions. The main challenges involve selecting dark, well-shielded locations away from light pollution for observations, as well as overcoming potential issues caused by weather conditions. Cloud cover, rain, or strong winds can hinder the collection of quality data. Particularly on cold October nights, when temperatures can drop to very low levels, it is important to take care of the equipment's safety and functionality, as well as ensuring comfortable conditions for observers, to maximize the efficiency of the instruments and not miss out on unique astronomical phenomena. When two bright comets appear simultaneously in the sky, it creates a spectacular and memorable show for viewers. Such events serve as excellent opportunities for schools, astronomy clubs, and public observatories to organize special events dedicated to comet observation. These gatherings help beginners learn about cometary science and celestial objects, while experienced observers can compare different types of comets, distinguished by their origins, structures, and behaviors. During these nighttime meetings, participants not only enjoy the beauty and wonders of space but also expand their knowledge of astronomy, fostering a greater interest in exploring the universe. It is worth noting that such initiatives promote scientific literacy and allow individuals of all ages and backgrounds to experience the wonder that space offers, understanding that these phenomena are accessible to everyone who is willing to look up and ask questions about the infinite universe. The willingness to go outside and observe the starry sky increases as October 2025 approaches. During this period, an unprecedented scenario of astronomical activity will unfold in the sky, leaving its mark on history. At the same time, an interstellar visitor will pass through the interstellar space near Mars, a rare and astonishing event that sparks particular interest among scientists and star enthusiasts. Ahead, a long-period comet will reach its peak brightness, becoming one of the brightest and most noticeable objects in the night sky in recent decades. In conditions of active solar weather, accompanied by solar flares and coronal mass ejections, as well as ongoing seismic tremors in Venezuela, these events create a complex and rich timeline that combines phenomena related to Earth's geology and interstellar astronomy. This convergence occurs against the backdrop of unusual coincidences and large-scale natural and cosmic phenomena. On the eve of October, two quite extraordinary space events almost coincided within a short time frame, creating the impression that everything happening was orchestrated according to a specific plan. First, a mysterious interstellar object passed through interstellar space, flying past Mars at a distance of just under 20 astronomical units. This flyby served as a reminder that our solar system is influenced not only by internal processes but also by external interstellar phenomena, which, despite their remoteness, can impact cosmic and terrestrial dynamics. At the same time, in October, the comet Swan approached Earth, reaching its closest approach, coinciding with the new moon, a moment when the moon nearly completely obscures the sun, plunging the Earth into shadow. This period was also marked by the peak of the Arietid meteor shower, which, breaking apart in the atmosphere, created a spectacular meteor rain that delighted astronomy enthusiasts. Simultaneously, in the distant depths of space, approximately 136 astronomical units from the Sun, the object 3I Atlas reached its perihelion, the closest point of its orbital path to our star. All of this occurred within a short span of time, creating the sensation that these events are intricately connected. Collectively, they formed a dramatic tableau, as if specially staged to draw attention to the mysteries of space and our planet. Over several days, two powerful stellar explosions occurred in the sky, accompanied by bright flares and energy discharges, and within a few hours, two major earthquakes shook the Earth, reminding us of the planet's internal forces. During the same week, solar storms swept through space, causing geomagnetic vortices and magnetic storms on Earth. All of this, the approach of the interstellar object to Mars and the simultaneous peak brightness of the comet, seems less like mere coincidence and more like something much greater, extending beyond randomness. Such a convergence of events prompts reflections on the so-called cosmic synchronicity, a remarkable harmony in a world where, seemingly, random phenomena suddenly begin to appear interconnected. The human brain, by its very nature, is evolutionarily tuned to seek patterns in the surrounding world. This ability has helped our ancestors survive, recognize threats, and identify opportunities based on subtle links between the environment and internal states. Our cognitive architecture automatically and often unconsciously searches for connections that may indicate cause and effect relationships, even when only a coincidental correlation exists between events. As a result, the habit of finding patterns and meaning in chaos takes on a dual character. On one hand, it helps detect important signals and make predictions. On the other, it can lead to false conclusions and overinterpretation of random coincidences. This tendency, while a powerful tool, also represents a weakness of human perception. Historically, the skill of recognizing patterns helped our ancestors predict seasonal changes, weather conditions, social dynamics, and animal migrations. However, today, the same ability can cause us to perceive non-existent connections and find meaning where there is none in reality. For example, noticing a coincidence between periods of increased solar activity and earthquakes might lead us to believe in a direct link, although scientific research has yet to confirm such a relationship. Within the scientific community, there is a clear and well-understood consensus. There is currently no evidence of a physical mechanism capable of linking space weather phenomena with earthquakes. Decades of research in this area have attempted to find correlations between solar activity and seismic events, but none have been conclusive. These events most often occur during periods when solar activity reaches its peak, making the late 25th year particularly likely for the emergence of various phenomena. The interaction between powerful solar storms, coronal mass ejections, and cometary material is a well-studied area of plasma physics, not something exotic or inexplicable. At the same time, acknowledging scientific fundamentals does not mean ignoring the astonishing and sometimes poetic nature of such temporal clusters of events. Sometimes, the universe seems to play along with our expectations, creating situations where randomness takes on poetic qualities, even when the mechanisms behind these phenomena are ordinary, understandable, and consistent. The task is to preserve space for both approaches, skepticism and genuine wonder. This balance allows us to evaluate statistical clusters of events without exceeding the boundaries of scientific inquiry, while remaining open to the sense of wonder inspired by the beauty and complexity of the universe. We can acknowledge that the appearance of double new stars reaching their visible brightness within a matter of days is a rare and intriguing phenomenon, not necessarily causally linked to earthquakes or other geophysical events. At the same time, we can understand that earthquakes with a magnitude of 6, occurring within a few hours in the same region, follow well-known patterns of stress transfer in the Earth's crust and the sequence of aftershocks, without implying any influence from space weather or sudden cosmic forces. And finally, we can experience awe when witnessing the coincidental timing of the bright comet 3I Atlas approaching the Sun during the solar maximum. It is important to recognize that such coincidences are more about facilitating observation and study rather than mystical synchronicities or signs from higher powers. We can rejoice that two bright comets appeared in the same region of the sky at an optimal moment for observation, without assuming that cosmic forces deliberately arranged this alignment for human pleasure or scientific discovery. However, in the media, such coincidences are often amplified, creating the impression that everything happening is interconnected and holds profound meaning. Intensive coverage of several dramatic events in a short period, active discussion on social media, these all generate an echo effect, heightening the perception of their significance and creating the illusion that these phenomena are linked and have hidden meanings. As a result, it seems as though all these events are occurring right now to capture our attention, though in reality, they may be purely coincidental. The psychological impact of such repeated coverage and amplification can lead even random clusters of phenomena to appear far more important and meaningful than what statistical studies and scientific analyses actually confirm. Historical and archaeological evidence shows that humans have always sought signs and messages from above in earthly events. In ancient cultures, comets were seen as omens of fate-changing events, eclipses as manifestations of divine will or wrath, and the coincidence of earthquakes with the appearance of bright comets as supernatural signals sent from the heavens to humanity. Although these cultural models have become outdated with scientific progress, they continue to persist to this day. In the modern world, they coexist with scientific knowledge, satisfying deep psychological needs for meaning and connection in seemingly random and disconnected events. The main challenge lies in maintaining a balance between scientific rigor and the ability to appreciate the emotional and aesthetic aspects of such remarkable connections. We can value the beauty and harmony of cosmic time without abandoning critical thinking and rational analysis. Ultimately, we can experience genuine wonder and admiration at the random arrangements and coincidences in the universe. A reasoned consideration of competing hypotheses involves the simultaneous existence of various theoretical approaches. However, it is crucial to clearly distinguish between verified scientific knowledge and speculative assumptions that have yet to be confirmed. All interpretive activity must be grounded in solid physical principles and fundamentals, rather than unverified guesses. For example, explaining stellar phenomena is based on modern theories and observational data, such as stellar physics and nuclear reactions within stars. Similarly, plate tectonics provides a scientifically grounded understanding of the processes causing earthquakes on Earth, while solar physics explains the mechanisms behind coronal mass ejections and solar flares, as confirmed by numerous satellite observations. Orbital mechanics, in turn, allows for precise predictions of comet approaches and trajectories, validated by long-term astronomical measurements. Each of these phenomena obeys well-known and tested laws of nature, functioning independently. These are the fundamental pillars of modern science. In contrast, interpretations related to cosmic resonance or hypotheses about subtle connections between different phenomena venture into more speculative territory. Such ideas suggest complex and often unconfirmed relationships between phenomena that have not yet been recognized or understood by the mainstream scientific community. In this context, it is not a contradiction with physical science but an expansion of understanding, implying that our current knowledge is only part of a broader picture. Perhaps, future in-depth research will reveal genuine correlations between seemingly unrelated fields of knowledge. Therefore, both perspectives, established science and speculative hypotheses, can coexist peacefully in the intellectual sphere, provided we clearly delineate between confirmed facts and hypotheses while remaining open to new discoveries. The significance of verified science is rooted in its reliable foundation of extensive observations and its successful ability to make accurate predictions, as confirmed by numerous experiments and observations. At the same time, speculative ideas deserve attention and study if they remain clearly separated from verified knowledge and generate testable hypotheses. This is important for the development of scientific thinking and the search for new ways to understand the world. In this context, the autumn equinox season holds particular significance, as it creates an additional, logically connected framework for studying natural phenomena. During this period, an effect known as the McFerrin phenomenon is observed, geometric conditions that amplify the influence of space weather on Earth in September and October. This makes the autumn months more likely times for significant geomagnetic storms and related phenomena. In some regions, seasonal patterns in earthquake frequency have been recorded, although the mechanisms behind these correlations remain incompletely understood, and the effects observed are often minor. In the cultural sphere, archetypal models provide rich material for storytelling, without requiring literal interpretation. For thousands of years, comets have symbolized change, upheaval, as well as cosmic interaction and communication between worlds across various cultures and traditions. Earthquakes have been perceived as manifestations of the internal dynamics of Earth's solid rocks, as expressions of its living, moving core. Meanwhile, stellar explosions are seen as demonstrations of wild beauty and the continuous development of cosmic evolution, reminding us of the power and infinity of the universe. These archetypal associations create a rich palette of narrative elements that resonate deeply within human psychology, while remaining outside the strict physical causality framework. They evoke strong emotional and symbolic associations that underpin many cultural narratives and myths. This wealth of imagery allows for the exploration of cosmic events. Science advances through consistent, carefully planned observations, hypothesis formation, and rigorous testing of these hypotheses to eliminate premature confidence regarding complex and diverse phenomena. The period when the calendar months of September and October act as a special temporal segment of the year is particularly important, providing rich material for in-depth analysis and research from both scientific and more imaginative, speculative perspectives. It is crucial to maintain a clear and precise distinction between what we observe directly, what we hypothesize based on these observations, and what we can confidently assert as established facts. When delving into these complex issues, it is especially interesting to focus on one particular hypothesis, which, despite its controversial nature, deserves closer examination. This is the idea that space weather, that is, changes in solar activity and related electromagnetic phenomena, may influence Earth's seismic activity. Initially, this hypothesis remained a topic of debate and speculation for a long time because the mechanisms linking space activity and terrestrial processes are poorly understood and often cause skepticism. Part 12 is dedicated to discussing the interaction between space weather and earthquakes, where the possibility is considered that solar storms, especially during periods of heightened activity, might somehow contribute to the occurrence of terrestrial disasters through mechanisms that remain insufficiently understood and explainable within the framework of modern physics. The idea that solar storms and related electromagnetic disturbances could influence the Earth's crust occupies one of the most controversial and persistent positions in scientific debates concerning the Earth's interaction with space. For many decades, scientists have observed and recorded statistical correlations between various manifestations of space weather, such as solar flares, coronal mass ejections, and solar wind streams, and the level of seismic activity on our planet. However, despite these observations, no existing and widely accepted physical mechanisms have been able to fully explain how electromagnetic disturbances, propagating over millions of kilometers, could trigger sudden fractures and catastrophic earthquakes in the Earth's crust. Today, this remains one of the most intriguing and debated mysteries in modern geophysics and space science. One of the most recent and somewhat astonishing hypotheses proposed by scientists is the idea put forward by researcher Stephen Burns. He suggested that a significant decrease in solar wind density following the passage of high-speed streams, known as coronal or solar streams, could lead to the formation of a kind of electromagnetic vacuum. According to him, this vacuum could subtly and gradually alter the stress fields within the Earth's crust, ultimately contributing to the formation of faults and earthquakes. According to Burns' model, when dense, fast solar wind suddenly gives way to a more rarefied and slower background solar wind, this change in electromagnetic pressure affecting Earth's magnetosphere could, in theory, propagate through complex coupling mechanisms, influencing stress accumulation processes in fault systems within the Earth's crust. This chain of cause and effect involves several stages, each associated with certain uncertainties and the weakness of the proposed effects. To begin with, variations in the density of the solar wind over specific periods influence the configuration and pressure of the magnetosphere, the magnetic bubble surrounding our planet, which acts as a shield protecting Earth from most adverse space weather phenomena. Changes in the shape and strength of this magnetic bubble can alter the electric currents flowing through the ionosphere, the upper, conductive layer of Earth's atmosphere. These changes in solar activity, in turn, may influence various Earth processes. Currently, there is a vast amount of scientific literature claiming the existence of certain correlations between different aspects of cosmic activity and seismic activity on Earth. However, there is virtually no convincing evidence of a causal relationship between these phenomena. For decades, scientific studies have published data on statistical correlations between solar activity and earthquake frequency, between the intensity of geomagnetic storms and clusters of seismic events, as well as between various space weather indices and regional earthquake catalogs. These correlations often appeared statistically significant in initial analyses. However, subsequent tests conducted over different time periods, across various geographic regions, or using updated earthquake catalogs frequently showed that they disappear or become statistically insignificant. One reason for this is publication bias, which significantly complicates an objective assessment of the existing data. In simpler terms, positive results indicating a link between space weather and seismic activity are much more likely to be published, accepted, and cited than results that show no such relationships. This creates the illusion of a broad scientific consensus, although in reality, such connections may not exist at all or may be so weak that they are difficult to detect through rigorous analysis. Meta-analyses, studies that combine results from multiple individual works, show that as the volume of data increases and methodological rigor improves, the apparent effect diminishes. In other words, when larger datasets are collected and more stringent statistical methods are applied, most previously identified correlations either disappear or prove to be statistically insignificant. The official stance of authoritative organizations such as the United States Geological Survey and International Seismological Institutes is that no reliable evidence of a connection between space weather and earthquakes has been found. This view is supported by extensive statistical analyses of global earthquake catalogs, as well as comparisons with detailed space weather databases covering several solar cycles. When methods accounting for multiple comparisons, temporal groupings, and systematic sampling errors are used, most initial correlations either vanish or demonstrate their insignificance from a statistical perspective. Nevertheless, some researchers continue to explore potential more subtle and complex relationships that might only manifest under specific conditions. For example, changes in atmospheric pressure associated with geomagnetic storms could theoretically influence the stress levels in fault systems, since pressure in these zones can fluctuate. However, in most cases, such pressure variations are less than 1 millibar, which is significantly lower than the typical pressure changes caused by weather conditions, and these variations, in turn, do not show clear correlations with seismic activity. Regarding another proposed mechanism, electromagnetic induction, it is based on the idea that strong geomagnetic storms can induce electric currents in conductive materials such as underground water systems or minerals. Theoretically, these currents could alter electrochemical processes in fault zones, which might influence steam pressure or the strength of rocks, potentially triggering or delaying earthquakes. Nevertheless, despite the existence of such hypotheses and possible mechanisms, the scale of these effects appears insufficient to significantly impact the main seismological processes, which are already well studied and confirmed by numerous observations. Overall, although theoretical mechanisms exist, their actual contribution to earthquake initiation or alteration of their characteristics remains highly doubtful and seemingly negligible. The study of gravitational effects offers scientists much more promising avenues for interaction with space than those based on electromagnetic mechanisms. In particular, the influence of Earth tides caused by changes in the gravitational fields of the Moon and Sun is a well-studied and easily measurable phenomenon. These tidal forces directly impact the Earth's crust, causing small but significant stresses, which, according to numerous studies, can facilitate the occurrence of earthquakes. During periods when tidal stresses reach their maximum, there is a slight increase in seismic activity, as confirmed by statistical data. It is important to emphasize that the mechanisms by which these gravitational effects operate are well understood. They manifest through physical processes that directly alter the stress state in Earth's fault systems. These processes are well explained by classical physics and are supported by precise measurements, making them one of the most reliable and comprehensible factors influencing earthquakes. However, a question arises: could similar gravitational effects from other astronomical objects and sources also influence seismic activity on Earth? Within this hypothesis, possible impacts of planetary alignments and conjunctions are considered, which, although attracting attention in some alternative theories, exert gravitational influences that are orders of magnitude smaller than lunar tides. Even large planetary alignments, such as oppositions or conjunctions, generate tidal forces, but their impact on our planet is extremely weak. These forces do have an influence, but their amplitude is significantly lower than those caused by the Moon and the Sun, and they cannot account for a substantial portion of earthquakes. In reality, tidal oscillations induced by the largest planets, such as Jupiter or Saturn, exert only minimal effects compared to the familiar lunar-solar tidal influences, and their impact on processes within the Earth's crust is considered negligible. The challenge in verifying the connection between space weather and earthquakes lies in the complex necessity of distinguishing genuine physical relationships from statistical coincidences. Earthquakes are phenomena driven by intricate patterns, including sequences of aftershocks, spatial clustering, and temporal correlations. These patterns can easily create false, seemingly meaningful links with external changes that occur over time. Conversely, indices of space weather, such as measures of solar activity or interplanetary magnetic fields, also exhibit autocorrelation, periodic fluctuations, and data clustering, which can give rise to illusions of correlation with seismic activity. These are purely statistical coincidences. Therefore, establishing true causal relationships requires specially designed studies where hypotheses, time intervals, geographic regions, and statistical methods are predetermined and fixed before data analysis. Such approaches, involving strict protocols of blind testing, help reduce bias and ensure objectivity of conclusions. In these methods, researchers analyze earthquake catalogs without prior knowledge of the current state of space weather, helping to eliminate subjective factors and distortions. These rigorous standards demand significant effort and are rarely found in modern scientific literature. However, they are essential for confirming or refuting hypotheses about the existence of a real connection between space weather and seismic processes. The fundamental mechanism underlying the hypothesis of this relationship must not only be hypothetical but also validated through experimental or theoretical foundations. Primarily, it is necessary to demonstrate that this mechanism is feasible within the laws of physics, such as through laboratory experiments or computer modeling. These studies should demonstrate the possibility that electromagnetic or other partial effects related to cosmic phenomena may influence seismic activity. Recent consecutive earthquakes in Venezuela have occurred under conditions of heightened space weather activity, prompting ongoing reflections and discussions about potential correlations between these two phenomena. However, it is important to emphasize that isolated coincidences, even impressive ones, do not constitute definitive proof of a systematic, consistent relationship. Overall, the geological situation in this South American country is shaped by its location in a highly tectonically active region, where earthquakes of magnitude 6 occur irregularly but with some predictability based on the dynamics of tectonic plate boundaries, fault characteristics, and models of stress accumulation in the region. If a genuine, significant connection between space weather and earthquakes existed, it would most likely manifest as a very subtle and conditional effect rather than a clear, dramatic, and universal cause. In most cases, such influences might only play a role in fault systems already on the verge of failure, where even minimal additional stress changes could trigger a rupture, whether hours, days, or weeks later. In other words, space weather cannot directly cause earthquakes that would not have otherwise occurred. It can only act as a factor that amplifies existing tendencies. Modern scientific perspectives on earthquake mechanisms suggest that their precise timing is primarily determined by the evolution of local stress fields, the properties of fault zones, and stochastic processes occurring within complex nonlinear systems. In this context, external influences, be they space weather, atmospheric pressure, or other factors, play a minimal role compared to the dominant tectonic forces, which slowly accumulate stress over decades and then suddenly release it during major faulting events. The most honest and balanced scientific stance recognizes the possibility of both theoretical prerequisites and empirical limitations for such connections. The hypothesis of subtle electromagnetic or gravitational effects of space on Earth processes cannot be entirely dismissed. However, to date, there is no convincing evidence that these influences reach sufficient amplitude to significantly impact earthquake occurrence. Future research in this area should focus less on seeking statistical correlations between observed data and more on developing physical models capable of explaining potential mechanisms of interaction between cosmic factors and terrestrial processes. Only by understanding the physical fundamentals can we speak about the actual likelihood of external influences on seismic activity. In practical terms, for risk assessment and earthquake preparedness, monitoring space weather is not a useful tool, as it does not provide specific data on seismic hazards. Based on established seismological knowledge, it is necessary to rely on historical earthquake models, fault system analyses, probabilistic seismic hazard assessments, as well as on developed building codes and emergency response plans. All of these offer a more reliable and tested basis for protecting populations and infrastructure than hypotheses about the influence of space weather. As research in this area deepens, an even more hypothetical question arises, which, although seemingly far removed from immediate practice, still deserves attention. Namely, could the energy released by distant stellar explosions somehow influence Earth's climate or geological processes occurring on our planet, over timescales exceeding human generations? This idea, in essence, is based on the hypothesis that extremely powerful energy sources, supernovae located hundreds, thousands, or millions of light-years away, could, in a theoretical model, affect our planet's atmosphere and climate. Unlike hypotheses about the connection between space weather, which implies short-term and localized effects, the energy from supernovae involves vastly greater distances and energies. Ordinary new stars, such as V1935, Santa, or V7994, are astronomical objects that, compared to our bright, well-known stars, possess significantly lower energy output and are located much farther from Earth. That is why any short-term terrestrial effects related to their outbursts are practically impossible or so minuscule that they cannot be noticed in everyday life. To understand the scale of the involved processes, one must rely on the precise calculations of astronomy. Typically, a new star, during its bright outburst, releases an energy roughly equivalent to what our Sun emits over 10,000 years. This energy amounts to about 10 to the power of 20 joules, which sounds very impressive even to human perception. On the scale of our civilization, this amount of energy could sustain our needs for billions of years at current consumption rates. However, despite this, the energy released by such a stellar explosion propagates spherically in all directions, and as it moves away from the explosion site, its concentration depends directly on the distance. It disperses according to the inverse square law. For example, consider an object called V1935 Santa, which is most likely located several thousand light-years away from Earth. Its explosion occurred thousands or even millions of years before humans, their writing, agriculture, and permanent settlements appeared on Earth. At the time this ancient stellar catastrophe took place, humanity could not even imagine that such a powerful burst had occurred in the distant universe. By the time its light and energy reach our solar system, their levels have already diminished to the point that their influence on Earth's climate or atmosphere becomes practically imperceptible. Essentially, the energy reaching our planet in that month is probably only a few additional photons per square meter of surface, less than the brightness of a bright light bulb held at arm's length. To put this into perspective, considering the total amount of energy from new stars during their flare periods, these levels are so small that they cannot even slightly warm a single cup of coffee, let alone cause global climate changes. For comparison, supernovae, explosions that can genuinely impact the climate on geological timescales, should be mentioned. For instance, a supernova occurring about 50 light-years from Earth can release such a large amount of high-energy radiation that it could potentially significantly alter the chemical composition of the atmosphere. In particular, gamma rays and X-rays emitted during such an explosion can destroy large sections of our planet's ozone layer, leading to increased ultraviolet radiation reaching Earth's surface. This state, in turn, could trigger mass extinctions, as high doses of ultraviolet radiation negatively affect living cells and ecosystems. Some scientists have even proposed hypotheses linking nearby supernovae to historical mass extinctions that occurred in the distant past. Specifically, it is suggested that an event approximately 450 million years ago coincided with a supernova activity in a neighboring part of the galaxy and may have contributed to global ecological changes. However, establishing a precise causal relationship between cosmic catastrophes and biological crises remains very challenging. It requires extraordinary evidence, which has not yet been obtained. The mechanisms by which supernovae influence climate and atmosphere are not limited to mere thermal heating but include complex processes related to changes in the chemical composition of the air, the impact of ionizing radiation, and the destruction of the ozone layer. These consequences can have long-term and irreversible effects on life on the planet, making the topic of their influence extremely important and of great interest to scientists. High-energy photons emitted from stellar explosions have the ability to penetrate the upper layers of Earth's atmosphere, where they can cause dissociation of nitrogen and oxygen molecules. This process leads to the formation of nitrogen oxides, which subsequently act as catalysts in the destruction of the ozone layer. A thinning ozone layer means that significantly more ultraviolet radiation from sunlight will reach the planet's surface. This increase in ultraviolet flux could potentially impact ecosystems worldwide, from microscopic organisms in the ocean to terrestrial animals and plants. All of this may trigger complex feedback loops that ultimately alter global climate processes. In addition, there is another possible channel through which cosmic phenomena can influence Earth: the interaction of cosmic rays with the atmosphere. Although this mechanism is not yet fully understood, it is believed that cosmic rays, which are high-energy particles accelerated by shock waves from supernovae, can influence cloud formation. These particles can serve as condensation nuclei around which water droplets form, thereby affecting the planet's cloud cover. Theoretically, changes in the intensity of cosmic ray flux could lead to redistribution of cloudiness and, consequently, to shifts in the global climate. However, it is important to note that experimental evidence supporting this mechanism remains limited and is a subject of considerable debate among scientists. Regarding the new stars that appeared in September, their contribution to the overall cosmic ray background is considered negligible on an astronomical timescale. Their direct influence on Earth's space environment is virtually imperceptible. For cosmic rays accelerated by events such as supernovae to reach our planet, they would need at least thousands of years to traverse interstellar space. In this case, they would be indistinguishable from the general galactic background radiation, and their impact on Earth would remain virtually unnoticed. The media often confuse different types of stellar explosions and their supposed effects on our planet. Some publications hastily conclude that supernovae can significantly influence climate processes or trigger earthquakes, which often leads to distortions of scientific facts. Typically, such headlines do not distinguish between nearby supernovae, which under certain conditions could have a noticeable impact on geological processes over millions of years, and more distant, far-off stars whose explosions are incapable of exerting any real influence on Earth's climate. This misunderstanding contributes to the spread of sensationalist astronomical models, where dramatic scenarios are placed above rigorous scientific accuracy. The idea of a possible connection between stellar explosions in September and earthquakes is particularly popular, fueling the desire to find patterns in the chaos of natural phenomena. However, the scale of energy involved in such processes makes any attempt to establish a direct causal relationship completely impossible from a physical standpoint. The total energy that could ever reach Earth from both new stars over their entire existence is less than 1 second of sunlight falling on the planet's surface. Scientific investigation into the correlation between stellar explosions and climate change is a well-founded, fascinating, and promising field of research, provided it is conducted within realistic scales and considers probable mechanisms of influence. Only with such an approach can misconceptions and incorrect conclusions based on coincidences or guesses be avoided. Ultimately, it is important to remember that although space does influence our planet, this impact occurs on very small scales and over very long periods, requiring patient and careful scientific analysis. Scientific studies show that the rate of supernova explosions in our galaxy is approximately 1 to 3 events per century. This means that Earth has periodically been exposed to high-energy radiation from nearby stellar explosions over millions of years of its geological history. Such events in space sometimes lead to the release of enormous amounts of energy and particles into the interstellar medium, which, upon reaching Earth, can leave noticeable traces in the form of radioactive isotopes in the planet's geological layers. Among these indicators, the isotope IRON-60 holds particular significance. It is a radioactive isotope primarily formed during supernova explosions. Its detection in deep ocean sediments and ice cores provides direct evidence that Earth has periodically experienced increased bombardment by cosmic rays originating from stellar sources. These traces, preserved as specific isotopic signatures, offer a unique opportunity to trace how such cosmic events could have influenced our planet over millions of years. However, it is important to emphasize that these impacts occur over very long geological timescales and do not have a noticeable effect on climate or biological evolution in the short term. The discovery of IRON-60 suggests that approximately 2.5 million years ago, Earth may have experienced heightened exposure to cosmic rays, possibly linked to supernova activity in nearby young stellar associations. The question of how such periods of heightened radiation activity might have influenced the planet's climate conditions, atmospheric chemical composition, or biological evolution processes remains an active subject of scientific research and debate. Some theoretical hypotheses link changes in cosmic ray fluxes to glacial cycle patterns. However, these hypotheses have yet to be convincingly proven. Overall, the impact of cosmic events on Earth's climate over a historical timescale remains a matter of speculation and scientific conjecture, and any assumptions about their significant influence are primarily of a theoretical nature. Regarding more recent times, the last 225 years, any hypothetical effects of supernovae in space on Earth's climate system are considered purely academic and practically negligible. These distant stellar explosions are incapable of exerting a noticeable influence on our planet's radiation balance, altering the atmospheric chemical composition, or causing significant climate shifts. Instead, they serve as excellent examples of how remarkable and powerful stellar evolution is, and how nature creates phenomena associated with explosions at cosmic distances, processes observed from safe and well-understood vantage points. Thanks to these phenomena, scientists have a unique opportunity to study the physics of explosions and stellar evolution without risking their safety. The main lesson to be drawn from this entire picture is the importance of maintaining perspective, recognizing the vast scales of the universe, and understanding the difference between grand cosmic events and their actual impact on our planet. In our universe, spectacular phenomena occur regularly: star explosions, galaxy collisions, black hole mergers, which release colossal amounts of energy. However, most of these events remain too distant or too brief to have a significant effect on Earth's climate processes. Primarily, our planet is shaped by internal factors such as variations in solar radiation, atmospheric composition changes, ocean circulation patterns, and volcanic activity. All of these are processes occurring over timescales ranging from years to thousands of years and beyond. Although hypotheses about the influence of exotic astronomical factors on Earth's long-term geological evolution are not excluded, their role remains minor compared to the dominant internal mechanisms. Thus, the psychological appeal of the idea linking distant stellar explosions to terrestrial phenomena reflects a deep human need to find meaning and patterns in seemingly random events. This tendency to seek connections and causal relationships has long helped our ancestors recognize genuine ecological patterns, enabling them to better understand and adapt to their environment. However, at the same time, this tendency can also mislead us, causing us to perceive random or unrelated phenomena as important and significant, which sometimes leads to erroneous conclusions and incorrect interpretations of events. In the context of studying space and terrestrial phenomena, our attention increasingly turns to the interstellar visitor, which can provide the most immediate and clear example of how our solar system interacts with matter arriving from other star systems. This object becomes a kind of bridge between space and Earth, opening up unique opportunities for scientific research. Part 14. Interstellar visitors as solar probes are not just curiosity driven by interest in interstellar space. They are potentially the most sensitive natural instruments ever created for studying the interaction of our Sun with material formed around other stellar objects. Unlike previous interstellar objects, such as Oumuamua, which passed by too quickly for detailed study, or Borisov, which remained at a relatively distant range throughout its transit, this third interstellar guest offers unique opportunities to observe how solar weather influences matter that has traveled for millions of years through interstellar space between different star systems. Its geometric trajectory makes it especially valuable for heliophysics, as it crosses the ecliptic plane, the very plane where all the planets of our solar system are located. In this region, the density of solar wind, the intensity of the magnetic field, and the activity of space weather reach their peak values. Its approach coincides with the peak of the 25th solar cycle, when the intensity of coronal mass ejections reaches a maximum, and the structure of the solar magnetic field becomes particularly complex and chaotic. Imagine comets as natural magnetometers and plasma diagnostic tools freely floating in space. Their ion tails serve as visual confirmation of the existence of invisible magnetic field lines embedded in the solar wind. Changes in the orientation, brightness, and morphological structure of these tails provide scientists with crucial information about the solar wind speed, the density of its magnetic field, the direction of magnetic lines, and the passage of shock waves or other disturbances. Professional space weather researchers have been using comets in our solar system as natural sensors for decades, extracting quantitative data on the conditions of space plasma from their observations. They analyze this data to understand how solar activity influences the environment and how the state of interplanetary space changes. However, the appearance of an interstellar visitor, such as this third object, significantly broadens the scope of research, enabling the study of materials whose origins and chemical compositions differ markedly from those of comets in our own system. While comets formed from the same primordial disk as our planets contain volatile substances that originated during the formation of the solar system billions of years ago, the interstellar visitor carries traces of materials that formed around a completely different star, in another stellar system, possibly billions of years ago. This unique combination of materials, with its distinct history and chemical makeup, provides scientists with invaluable information about interstellar processes, conditions, and chemical diversity that existed beyond our system. As a result, each such interstellar visitor becomes a kind of envoy from another world, revealing the secrets of cosmic processes and expanding our understanding of the origin and evolution of matter in the vast expanse. Considering the influence of coronal mass ejections on the Sun's behavior and its surrounding environment, we are today witnesses to a unique phenomenon, the first recorded case of interaction between the magnetic field of our stellar neighbor and matter located outside the solar system. This interaction is observed at the moment when Mars, unusually close to the Sun, passes at a distance of only about 28 million kilometers from it at the beginning of October, which is roughly 1/19 of an astronomical unit. Such a close flyby creates exceptional conditions for astronomical research, which cannot be replicated with ground-based telescopes, as Earth's atmosphere significantly limits the capabilities of high-precision imaging and observation. At this time, 3 spacecraft, the ExoMars Trace Gas Orbiter, monitoring trace gases in the atmosphere, and NASA's Mass Reconnaissance Orbiter, offer a unique opportunity to observe the object from a distance of approximately 28 million kilometers, roughly corresponding to a position in the 19th astronomical unit. These spacecraft, positioned in specialized orbits, provide viewing angles and resolution capabilities unavailable to ground observatories. For example, the High-Resolution Imaging Science Experiment, HiRISE, camera aboard the Mars orbiters is designed for highly detailed surface imaging. Although its resolution of about 30 kilometers per pixel is limited, it still allows for the identification of key structural features of the comet, such as the central nucleus and extended fragments. While surface detail of the nucleus remains beyond reach, this capability already enables distinguishing a compact, concentrated formation from more branched and diffuse structures characteristic of comets. What is particularly important is that simultaneous observations from orbital spacecraft and ground-based telescopes allow for parallax measurements, a method of determining distances and sizes of objects based on observing their positions from different viewpoints. This approach significantly improves the accuracy of estimating the size and activity of a comet or other celestial visitor compared to single observations made from one location. The spectroscopic capabilities provided by Martian orbital platforms enable the collection of additional valuable information. On board these spacecraft are spectrometers specifically designed to detect and analyze trace gases in the atmosphere of the comet or other cosmic objects. These instruments can identify molecular emissions such as carbon compounds, hydrogen, oxygen, and other volatile substances released as the object approaches the Sun. In particular, spectroscopy can reveal molecules corresponding to the so-called CNC code or other molecular species, providing direct confirmation of the chemical composition of the object. This analysis helps to understand how solar heating contributes to the release of volatile substances from interstellar ice that makes up the comet. All these data collectively offer a unique opportunity to understand the nature of the material constituting the comet or other visitor, as well as the processes involved in its activation near the Sun. At the same time, ground-based astronomical observatories around the world actively participate in organizing and coordinating observational activities. Organizations such as the Minor Planet Center of the International Astronomical Union and other professional astronomical communities conduct continuous monitoring of the object, tracking changes in its brightness, spectroscopic evolution, and morphological variations. All of this occurs in conditions where the object responds to changes in solar wind and solar activity during its approach to the solar system. These observations provide insights into how the appearance of the visitor changes, how its structure and activity respond to solar disturbances and streams of high-energy particles. Amateur astronomers also play a significant role in this work, as their persistence and observational skill complement professional research. Their visual estimates of brightness, as well as photometric measurements using CCD cameras and other imaging methods, enable continuous data collection necessary for detecting short-term variations in the object's luminosity. These fluctuations may be related to phenomena such as disintegration events, similar to what occurs with the object known as the 30th Asteroid Telescopic Center, or simply the 30th ATLS. If such events indeed occur, they will open a unique opportunity to obtain unprecedented information about how solar magnetic fields interact with matter in interstellar space. Such events may become key to understanding how differences in the chemical composition of substances within the solar system differ from the composition of interstellar matter. These differences in chemical and molecular makeup can lead to various ionization process schemes, as well as variations in the efficiency of magnetic coupling or the dynamics of their reattachment, which in turn allows researchers to explore fundamental aspects of plasma behavior under conditions that are inaccessible for laboratory experiments on Earth. Scientific questions related to such interactions go beyond the usual scenarios of space weather, as they concern deeper processes occurring in interstellar environments. The object known as the 30th ATLS bears characteristic isotopic signatures inherited from its parent stellar system, opening new avenues for studying nuclear fusion processes in stellar cores, enrichment schemes of matter through supernova explosions, and the overall chemical evolution in different regions of the galaxy. These signatures, released through solar heating, provide a unique opportunity for spectroscopic analysis of interstellar matter in close proximity, which was previously nearly impossible. The path of this object through various space weather environments, from relatively calm interstellar space to more intense and chaotic conditions typical of regions near the solar maximum, represents a natural experiment. During this process, it is possible to observe how cosmic radiation and magnetic fields influence interstellar matter over time. These observations help determine whether the chemical composition, physical structure, or volatile content of this object has changed under the influence of multi-million-year cosmic rays, compared to recently formed comets that are part of the solar system. Professional radio observations play a crucial role in this process. They can detect molecular line emissions that serve as indicators of internal temperature, rotation speed, and the sublimation pattern of matter as solar heat penetrates the core of the object. The use of very long baseline interferometry methods allows for resolving structural details of the comet, revealing whether its core is a single consolidated body or a loose collection of smaller components weakly bound by gravity. The observation period for this object coincides with advances in space weather monitoring and modeling, significantly expanding capabilities compared to the timeframes of previous encounters with interstellar visitors. Thanks to precise real-time measurements of the solar wind conducted by multiple spacecraft, as well as the use of sophisticated magnetohydrodynamic models of the propagation of cosmic magnetic fields and interstellar particles, a clearer and more comprehensive context is emerging for interpreting changes in the behavior of this object. All of this significantly surpasses the capabilities available to previous generations of astronomers observing similar phenomena. It is also important to note that the 30th ATLS can serve as a test case for assessing planetary defense capabilities, despite the fact that it does not pose an immediate collision threat to Earth. Its trajectory, brightness variations, and response to space weather conditions provide valuable data for testing methods of telescopic detection, orbit determination, and characterization of such objects. These methods and insights could become critically important if a potentially hazardous interstellar object were to approach our planet, requiring rapid and accurate assessment of its parameters and potential risks. Expanding our understanding of interstellar visitors has a significant impact on fields such as astrobiology and the search for extraterrestrial life beyond our planet. Considering the hypothesis that 3 interstellar bodies, or interstellar visitors, moving through our solar system contain organic compounds or other prebiotic materials brought from their star systems of origin, spectroscopic analysis of such objects could reveal whether these chemical components are fundamental building blocks of life, widespread throughout the galaxy. Such discoveries could fundamentally alter our understanding of how biological complexity might arise and develop in other star systems, providing crucial information about the frequency and conditions under which life originates outside Earth. Ensuring extended observability of these interstellar bodies until the early 2010s guarantees that research initiated from the first contact can continue and expand well beyond initial expectations related to their passage past Mars. In particular, the upcoming October 29th and especially December 19th, highlighted in bold in calendars, offer a unique opportunity for detailed study of this interstellar visitor, as it will continue to evolve under the influence of changing solar heating conditions. During these events, we can observe the interaction of the object with the solar environment, which will help us understand its nature, composition, and dynamics. Against the backdrop of preparatory activities for unprecedented observational opportunities in October, the simultaneous convergence of several factors, the approach of an interstellar visitor, conditions of the solar maximum, the development of advanced monitoring technologies, and global coordination of international teams, creates astonishing prospects for gaining new knowledge. This knowledge has the potential to radically alter our understanding of how stellar systems interact with interstellar space and how this influences the formation and evolution of bodies within our own and other systems. Expectations related to future discoveries are filled with hope that, in these moments, we will find answers to the most fundamental questions about our place in the cosmos and the nature of the universe around us. Part 15 is dedicated specifically to looking into the future, and October, along with upcoming dates such as the 23rd, 25th, 21st, and 29th of the month, occupy a special place in the astronomical event calendar. Do not forget to highlight December 20th in bold, as this date could become one of the key moments in understanding interstellar visitors, their interactions with space weather, and broader aspects of cosmic neighborhoods surrounding our solar system. Everything that happens during these times could provide answers to questions that have intrigued scientists and curious minds since humanity first pondered its position among the stars. One significant moment will occur on September 30th. On this day, the interstellar visitor named TRIO and the object, Atlas, will make their closest approach to Mars at a distance of approximately 1 astronomical unit, about 28 million kilometers from the red planet. This is the first time in history that such an event will occur, with an interstellar object passing within the orbit of Mars rovers specifically designed to study small bodies. Scientific organizations and space agencies, such as the European Space Agency and NASA, have adjusted their observation plans to capture this unique encounter, combining the capabilities of modern technology and interstellar matter. The geometry of the upcoming observations offers advantages unavailable in ground-based observations, as spacecraft orbiting Mars will be able to observe the object from various angles. This will help resolve existing ambiguities regarding the size, shape, and activity of the interstellar visitor, which previously could not be determined through single-point observations. Simultaneous measurements from Mars and Earth will provide parallax data, allowing us to more accurately determine the distance to the object and its physical parameters. Imagine that the encounter with the interstellar object is like a blind date with a mysterious guest from the distant depths of space, specifically, from Mars, whose name is associated with Harvard astronomer Avi Loeb. His role in this story is to evoke both excitement and a sense of uncertainty. It is as if navigating unknown trails and trying to understand what lies beyond the horizon is accompanied by warm feelings of anticipation and simultaneous bewilderment. In such conditions, when the high-rise camera, orbiting Mars as part of the Reconnaissance mission, is supposed to capture an image of an interstellar object, its resolution is approximately 30 kilometers per pixel. This means that, despite modern technology, it is still impossible to detail the surface of this mysterious body. The resolution is too coarse to discern the finest details, but sufficient to notice, for example, a compact comet core and its elongated, stretched structure. Under these circumstances, scientific expectations should remain realistic, as it is necessary to avoid illusions and disappointments, especially when the first preliminary results become available. since they are likely to show only limited but important constraints regarding the size of the object, its brightness variation, and spectral composition. The true magic lies in understanding how it evolves, not in creating perfect, vivid images as if from the pages of science fiction novels. The upcoming October 20th and 21st promise something special in the astronomical world. During these days, a comet designated C220R2S will approach Earth, reaching its closest approach at approximately 26/100ths of an astronomical unit. This is about 6 million kilometers, or slightly more than twice the distance from us to the Moon, making the event extremely significant for observers. This moment coincides perfectly with the new moon, when the moon is hidden beyond the horizon and does not interfere with observations, as well as with the peak of the annual Arietid meteor shower, creating unique conditions for observing not only the comet but also falling meteors, which will brightly streak across the dark sky. All these factors make the last days of October particularly favorable for astronomical observations, as the sky is at its darkest and visibility at its clearest during this period. The brightness of the comet, according to current forecasts, may range from magnitude 4 to 6, meaning that under good conditions, it can be seen with the naked eye in dark areas, and clearly observed through binoculars or small telescopes. However, despite all predictions, it is important to remember that the brightness of newly discovered comets with long orbital periods, passing through the inner solar system for the first time, is a very conditional concept. Their behavior depends on many factors, and predicting it with absolute certainty is very difficult. The comet we call Swan may delight observers with spectacular tails that make it memorable, or, conversely, disappoint if it does not display the bright attributes expected of such comets. In this case, it will simply remain a bright point against the night sky, and its unique features may never manifest. The coincidence of several significant astronomical events at the end of October creates a unique opportunity for comparative and comprehensive observations. During these days, astronomers and sky enthusiasts will be able to simultaneously track the interstellar object approaching Earth, observe a bright comet that will become one of the main spectacles of the season, and enjoy the magnificence of meteor showers caused by the Arietid rain. Collectively, all these phenomena will occur under the darkest and clearest sky conditions, facilitating their optimal perception and study. A particularly important date is October 29th, when our calendar marks a moment known as the maximum solar heating of the 3 perihelion distances, meaning the closest point in the orbit of this interstellar object. This keeps it outside Earth's orbit, which is farther from the Sun than our planet. However, this distance is still small enough to allow detailed ground-based observations during the late part of 2025. The entire network of professional astronomical observatories around the world is coordinated to conduct observation campaigns aimed at tracking changes in the object's brightness, its spectroscopic evolution, and morphological variations. All of this is done to understand how it responds to the peak solar heating caused by its approach to the Sun. On December 29, 2025, the interstellar visitor will reach its closest approach to Earth, coming within approximately 1/8 of an astronomical unit, or about 270 million kilometers. For comparison, this distance is less than the farthest position of Mars relative to Earth, creating excellent conditions for observations by both professional astronomers and amateur astronomers with small telescopes during the winter months. This extended observation window until early 2026 provides a long period for scientific research, which can continue even after the main excitement surrounding its flyby past Mars and perihelion has passed. Unlike the object named Oumuamua, which left the inner solar system too quickly for detailed study, this interstellar guest offers months-long opportunities for in-depth observations and analysis. During its evolution, influenced by changing solar heating and cosmic weather, scientists will be able to record variations and features previously inaccessible to detailed examination. However, to accurately understand what can be expected and what might be an overestimation, careful calibration of public expectations is necessary. Ultimately, comets and interstellar visitors are objects known for their unpredictability. They can significantly exceed all expectations or disappoint observers hoping to witness impressive spectacles with the naked eye. The most likely scenarios involve gradual changes in brightness, subtle spectroscopic evolution, and morphological variations that can be easily detected with modern telescopic equipment. Dramatic events capable of astonishing viewers without the aid of instruments are unlikely. Professional observations, in turn, can reveal structural details of the comet's development, tail formation, and responses to variations in solar wind. However, these discoveries typically manifest as scientific data and analyses rather than vivid visual effects capable of capturing the general public's attention. The most significant results are often associated with spectroscopic studies, which allow scientists to determine the chemical composition of the object, isotope ratios, and volatile content. These parameters provide the most comprehensive understanding of the interstellar visitor's nature, while visual transformations that generate media buzz remain considerably less striking and less informative. During periods of heightened solar activity, which occurs within the framework of the 25th solar cycle, there is an increase in solar activity levels, raising the likelihood of strong geomagnetic storms. These phenomena can lead to spectacular northern lights and impact modern technologies. The Space Weather Forecast Center of the National Nuclear Energy and Meteorology Administration continuously monitors solar activity using a complex of satellite systems and ground-based observatories to provide timely warnings of potential consequences of solar flares and related space weather. The model continues to carefully track the propagation of coronal mass ejections as they travel through the heliosphere, offering timely forecasts of when solar storms might begin interacting with our planet's magnetosphere, as well as with orbiting spacecraft around Mars and trajectories of space missions like TriAI Atlas. This enables specialists and space weather enthusiasts to prepare in advance for possible effects of solar activity. It is especially important for photographers capturing the northern lights and everyone interested in space weather to monitor special alerts issued by the SWPC service. These notifications warn of approaching geomagnetic storms, classified as G-class storms, events associated with increased solar radiation marked as S-class, and radio light flares designated as R-class. All these phenomena are capable of triggering noticeable polar activity even at lower latitudes than typically observed during calm solar conditions, which is especially relevant during periods of solar maximum. The combination of conditions characteristic of the solar maximum period with favorable geometry related to the equinoxes creates unique circumstances for the occurrence of bright and dramatic manifestations of space weather. In October and November, these factors together provide the best chances to observe unusual and impressive phenomena associated with the interaction of solar eruptions and Earth's magnetic fields. Meanwhile, seismic activity monitoring in Venezuela continues due to a series of successive tremors following the main earthquakes of approximately magnitude 6 and 2, as well as an earthquake reaching magnitude 6 and 3 at the end of September. Seismological experts maintain constant observation of regional activity, recording new underground tremors and their development. However, despite modern monitoring capabilities, there are no methods capable of reliably predicting whether larger and more destructive earthquakes will occur in the near future in this region. The tectonic structure of the boundary between the Caribbean and South American plates is complex and unstable, ensuring ongoing uneven and sometimes unpredictable seismic activity in this zone. At the same time, over geological timescales, such events are inevitable and essentially part of Earth's natural processes. Therefore, to protect populations and infrastructure, all construction measures, emergency response systems, and safety protocols must be based on proven seismological knowledge. Under no circumstances should predictions based on space weather or astronomical events be relied upon, as the scientific community currently lacks reliable methods for short-term earthquake forecasting. At the same time, monitoring continues for objects such as V1935 Curie and V7994 Sagittary, as these stellar explosions develop through their characteristic phases of brightness decline. Professional astronomers and amateurs worldwide actively participate in observing these objects, conducting photometry and spectroscopic studies that allow tracking the development of physical processes occurring within the newly formed stellar remnants. These studies demonstrate how flares and thermonuclear reactions evolve over months and even years after the initial explosion. Within such observations, the American Variable Star Observers Association plays an important role, coordinating efforts to standardize methods and protocols, which ensures the comparability of data obtained by different observers using various equipment. Detection of high-energy signatures recorded by satellites such as Fermi and Swift provides valuable information about particle acceleration processes within shock waves generated by these stellar explosions. In the coming months, any of the newly formed star systems may experience so-called dust formation episodes, leading to a temporary loss of the object's brightness. This occurs because microscopic particles formed during these events can obscure the light. Every phenomenon, manifestation of interstellar guest behavior, space weather activity, as well as seismic monitoring processes and the evolution of newly formed star systems, all these events are governed by physical laws that operate independently of which specific temporary cluster or sequence of events caught our attention at the end of September. These laws are constantly in effect, regardless of our observations and interpretations, and their influence can be seen in every aspect of cosmic activity. Nevertheless, what happened during this period deserves special attention and thorough documentation, as it serves as a vivid example of how the universe sometimes organizes several dramatic events across different fields within very short timeframes. The question that remains open and piques the interest of scientists and space enthusiasts is this cluster of events purely a matter of chance, or are there subtle physical connections that are still elusive to us, and we simply do not yet understand their nature? Or perhaps, it is just an inevitable manifestation of life in a constantly changing and dynamic universe, where such coincidences are part of its natural course, and our observations are the only way to attempt to grasp their meaning. All of this underscores the need for careful analysis of what is happening, avoiding sensational interpretations often imposed by mass media, and relying on credible sources of information such as scientific centers and authoritative organizations. In particular, NASA, the European Space Agency, the Center for Small Planets, the U.S. Hydrometeorological Center, and the Space Weather Forecasting Center provide up-to-date, continuously updated, and verified information about current events in space and on Earth. The participation of amateur astronomers and geologists in these studies opens broad opportunities to contribute valuable insights to the scientific community, while also allowing each of us to observe and enjoy the wonders of cosmic phenomena firsthand. Joint efforts in photographing comets, assessing their visual brightness, observing the polar lights, or recording earthquakes through established networks enable scientists and enthusiasts to directly participate in documenting this unique period of highly active cosmic and geological activity. A speculative question that increasingly arises in connection with this temporary accumulation of events is the following: do these phenomena truly represent something more than mere statistical coincidence? If what is happening appears unusual and even strange, and many observers feel just that, perhaps the reason lies in the fact that our familiar timescales, in which we perceive stellar evolutions, geological processes, solar activity, and encounters with interstellar objects, have intersected over a short period of time as if woven into an extraordinary configuration. Such an intersection of events is a rare phenomenon that perhaps occurs only once in a person's lifetime. It is important to emphasize that all these observations and analyses go beyond immediate impressions and continue in the subsequent months and years, because only after acquiring new data, spectroscopic studies from orbital Martian probes, spectral analysis, data on perihelia, and extended monitoring, will we be able to understand what truly happened. Then we will be able to objectively determine which of these events are interconnected and which are merely coincidental. This process will require time and patience, as a final assessment of this unique phenomenon will involve numerous thorough investigations, comparing the results with existing scientific theories, and establishing where the boundaries lie between physical reality and psychological projections. Ultimately, many years of painstaking work will be necessary to distinguish genuine physical connections from random coincidences and scientific facts from conjectures and speculation. Undoubtedly, at this moment, we are witnessing the convergence of various aspects of cosmic activity, from stellar flares and earthquakes to encounters with interstellar objects, covering scales that remind us that our life unfolds within a universe far more complex, dynamic, and interconnected than it may seem at first glance through everyday observations. It is always relevant to acknowledge that all these cosmic phenomena, processes, and events carry an element of uncertainty inherent in any complex system, for the nature of the universe is full of secret mechanisms and unpredictable changes. At the same time, one cannot overlook the unique human capacity to observe this vast cosmic space, measure its parameters, and ultimately seek our place among endless stars and galaxies. This ability stems from genuine curiosity and a desire to understand what lies beyond the horizon of known knowledge, as well as from the longing to grasp the meaning of our existence within the vast scales of the cosmos. In the process of this exploration, a person encounters endless opportunities for wonder and inspiration, as the universe constantly demonstrates its ability to amaze us with its vastness, complexity, and infinite expressions of creativity. It reminds us of our humility and the boundaries we are gradually expanding, opening up new horizons of knowledge and understanding. Sometimes, it seems to humble us with its grandeur, reminding us of how small we are and how much there is still to learn. Ultimately, perhaps the true essence of our story does not lie in whether these cosmic events are connected by some mystical or physical means. Rather, an important aspect is that we live in a unique era in history. This is a time when humanity, for the first time in its history, has the ability to discover, track, and carefully study astonishing coincidences and patterns that manifest across various fields of space and time. And it is precisely thanks to the development of modern technologies, scientific methods, and global exchange of knowledge that we can recognize such connections, which would have been inaccessible to any civilization in the past. This is the distinctive feature of our generation. We are among the first in time, though not in significance, capable of observing the cosmos and its mysteries so deeply and broadly that it would be impossible for any civilization that existed before us. Perhaps, it is precisely in this ability that our greatest chance lies, to realize that we are not alone in this boundless space, and that despite all uncertainty and complexity, our pursuit of knowledge and the discovery of new horizons makes us part of a grand process that continues endlessly in the depths of the cosmos.